Hello, everyone, and welcome. I am Agnes Winokur, and I'll be your moderator for today's workshop. I will be the first presenter today discussing strengthening the validity, reliability, and consistency of drug analysis reporting. First, I would like to do a disclaimer. The opinions expressed during this presentation are mine and do not necessarily represent the opinions of the Drug Enforcement Administration, the Department of Justice, or the United States federal government. I also do not have any financial interest to disclose, nor any affiliation with the manufacturer of the analytical equipment presented in this presentation. As illicit drug samples become more complex, a more comprehensive early warning system is needed. In recent years, there have been more than 1,200 different novel psychoactive substances reported in the UNODC Early Warning Advisory by governments and partner organizations. With drug samples becoming more polydrug and complex drug mixtures, the need for early warning systems based on real-time data is critical to secure public safety through better informed public and law enforcement response strategy, as well as rapid government scheduling efforts. The public needs to know the most current emerging drugs and their associated dangers. That need to know is for now and not in 6 months or even a year. This can only be achieved if we all work together through voluntary sharing information systems. We need to break the silos of information by encouraging real-time collaborations and communication among all stakeholders from multi-disciplines and multi-jurisdictions. Seized drug forensic labs, toxicology labs, forensic labs, medical examiners, coroners, there are many challenges in reporting, and we cannot begin to effectively overcome them until we know that what everybody's seeing and what everybody's not seeing. The rapidly sharing of information can let forensic labs know what is of interest to medical examiners, hospitals, and what seized drug labs are seeing can help toxicology labs know what kind of testing panels to implement, for example. Rapidly turning analysis into information for the greater good and sharing that information should be our focus. For reliable data sharing, we need to increase reliability on drug detection approaches, evaluating and expanding instrument capability for all labs, and also the method development for these complex mixtures. We need to increase the reliability and on identification approaches, such as evaluating reference materials, their availability, and if they're not available, exploring ways to share data. Also looking at the metabolic studies that are necessary, especially with the complex mixtures that are happening in today's world. Focusing on detection and identification increases validity and reliability of information that is being shared. With that increased number of substances of similar structures that generate similar or the same testing results, this is a critical, important key to have good reporting data. Through collaborations and partnerships, then we can build our collective capacity that will generate trust on our data collection systems, which then enable the monitoring and the scheduling decisions that need to be taken based on looking at data mining, looking at all of the statistical and demographics data that is available if we're all sharing information. The National Forensic Laboratory Information System, or NFLIS, was first established in 1997. This is a system where state and local laboratories, forensic laboratories, voluntarily share information. DEA has been working to update NFLIS to assist with some of the challenges associated with reporting, such as nomenclature. One of those things, one of the changes that are coming up is having a recommended nomenclature to be used as the data that's being entered into NFLIS so that it can be better data analytics can be generated. This is one of the advantages of having one centralized national system for all drug reportings. We're also looking at how to put even more information into NFLIS so that it's more comprehensive. So not just from state and locals, but you will see in the next few slides some of the other components that we can put data into NFLIS, and then now you have data upon data upon data. And that's how we start breaking the silos of information and expanding our data analytics capability. So in order to enable this communication among stakeholders, regardless of discipline and jurisdiction, if we are able to coordinate the data that's being right now generated in all the different organizations, all the different jurisdictions, and somehow get those into NFLIS, we have one national early warning system that can help not just law enforcement, not just public health, not just the hospitals and the private sector, the private forensic labs, but everybody is benefiting from having all of this information in one location. And then we can address some of the challenges there as the data that's coming in that's being reported, such as nomenclature, such as jurisdictional limitations. We can start looking at all of that data that's coming in together and addressing as those challenges come up that everyone can benefit from them. For example, right now for NFLIS, the data that's going in there are the state and the local labs from seized drugs that they are voluntarily sharing all of that information. We have now added for DEA data, DEA forensic drug analysis data to be added into NFLIS, and also some of the limited tox data that we have access to be added into NFLIS. And then now we have more information, but more needs to be done. We need to keep coordinating, talking, partnering, collaborating, so that now we can add hospital testing data in there, private forensic labs, medical examiners, poison control. All of that data is very, very important. Drug checking labs, DUI, the laboratories that are testing for samples driving under the influence. All of this data is so information to truly create an early warning system that can benefit the United States. And in this way, because sometimes you may see certain drugs appear in one area and not another yet. There's different times as they emerge in the different sectors. So the quicker that we share that information, the quicker that we can all start adjusting our testing, adjusting our processes to be able to detect and identify. In addition, we are able to collectively address some of the challenges that come in as these new emerging drugs are coming into our landscape, right? And more slides as we continue to discuss in this presentation, I think that will make it more apparent, the need for all of us to work collectively. So NFLIS, if you go to the NFLIS website, you're going to find there publications that are available to the public, what forensic laboratories are participating, toxicology laboratories, medical examiners. We also have a network for real-time communication where laboratories can ask questions, and then collectively we can assist with the identification of unknowns or some sort of limitation in the analytical process, that there might be a question, for example, extraction or something like that, and collectively we're helping each other. That has been rebranded to now from synth opioids to forensic, but soon there will be more information on that. It has been going to some rebranding, so it's been a little bit, as that process is being finalized, we will be having more and more alerts going from there as well and sharing even more information. As the data gets enhanced of what's going into NFLIS, there is a way for it to be available to the public. The public can go in and register to have query capabilities. This is new. And then through these queries, the public has access to aggregated data from NFLIS drug collection. Like I said, right now it's only state and locals and the federal, some limitation on some of the tox data is coming in, but the more that we keep partnering, the more that we keep collaborating, the more powerful that that NFLIS becomes, and that these queries become more comprehensive. So it's enhancing the data that all different organizations have. Here's an example of some of the changes that have already happened, where now DEA data is also there and can also be searched through DEA or non-DEA. And I know you can't see it very well, but you can, at the right-hand side, it can tell you the number of fentanyls for this particular example, requiring fentanyl. And it's available to be able to see what number, how many fentanyl samples have been seen. There's many different types of queries that can be done. Here's another example, and you can see the type of form that the samples are being found, the states, if there's multiple drugs. So we're trying to enhance NFLIS on the type of queries that are available, and then we're trying to also figure out how to have more consistent the data that's going in there, because it improves the capability and the analytics that you can do to the data. So those things are being addressed, whether it's nomenclature, like I said, jurisdictional requirements, where only certain substances might get reported based on the jurisdiction that this forensic laboratory may be working in. We're trying to come up with options that we will still be able to capture that information into NFLIS, and again, making things more powerful. Here's another example on some of the queries that can be done. Here's the top 25 national drugs, just a very quick query that was done. But we can also do it based on cities and different locations and states, and all kinds of ways that these queries can be done. This is all very valuable information. So just from January to October of 2024, we see that cocaine, fentanyl, methamphetamine have the highest counts, so the highest number of samples that have been reported into NFLIS. So I wanted to bring to your attention that reporting is as good as the foundation of the power of reporting to increase collective capability is based on the reliability and validity of the detection and identification of drugs that we can do in forensic laboratories across the country. The Trank Act saw that importance, and it focuses on research processes and techniques to identify and differentiate illicit drugs with xylazine or other synthetic opioids and novel psychoactive substances to reduce analysis time, and again, increase the capability of forensic laboratories, with the idea that in all of that reporting can be leveraged to help us get a better picture of what's happening in the United States. So I can't stress this enough. The power of reporting is based on being able to rely and have high validity on our processes and our methods that are being used to detect and identify. So with that, I do want to explain why is that important, right? What is because of in today's world, samples, the nature of samples have just changed. Things are now more polydrug. The mixture of the different drugs that are in the samples are even more complex, because the different substances are very much related in terms of chemical structure, which makes the ability of methods to separate them, to be able to differentiate between them, even more challenging. As that complex mixtures increase, the complexity, the instrumental capabilities of the laboratories now have to be evaluated, have to be increased. Reference material now becomes even more important, because now instead of 2, maybe you need 8 different substances, 8 different reference materials. That availability, that cost, that extra data, if it's a new substance, how do you even know that you have it? So these are all important analytical challenges that are needed that affect reporting, right? Not just the jurisdictional requirements and nomenclature, but also what have you already detected and identified? How many unknowns are we not pursuing, and are they important to be pursued? These are true analytical challenges that we really need to discuss and kind of focus on, and that's really what this webinar is about, we need to concentrate on that foundation that affects reporting, and then our capability to do data analytics to what is being reported. So let's talk a little bit more about what that means for our challenges in drug samples. So routinely right now in forensic laboratories, the instrument of choice is GCMS. So this is just a very basic routine approach just to illustrate some of the challenges that we have and why it's so important to concentrate on having a methodology that can do as many compounds as possible and as quickly as possible. So right now, if you have a sample that comes in, it's dissolved in a chlorinated solvent, filtered to remove some of the insolubles, and placed in a GCMS. It might get concentrated. Now, one of the things to mention is that the complexity is not of these drug samples in today's world. It's not just the polydrug, but also the concentration. Some of the synthetic opioids that are extremely potent and hazardous, they come in very, very low concentrations. So in order to be able to detect it, to be able to identify them, we tend to then look at our methodology, and in a GCMS, you're going to lower that split. So you might go to a 25-to-1 split to try to increase that response and the likelihood of getting either that fentanyl analog, for example, and getting that molecular ion so that you can report it, right? So that you can identify it and then report it. If it doesn't meet that acceptance criteria or the fragmentation, then you might have to move to another technique, right? You might also have some challenges there as these different polydrug samples have substances of very similar structure. If it's a GCMS, you might have some that not only coalute together, but also have similar spectra. So if you move to another technique, so if you were in the GCMS and you lower the split and you still weren't getting that molecular ion, you might go to other techniques. Some of the other techniques might be a GCIR, which is a gas chromatograph with an infrared or an NMR. But these also have their own limitations because of sensitivity, and there's ways to overcome. This is just a very basic illustration of some of the things that happen every day in a laboratory. One of the things is you have something of very low purities that you may need to have ways to make it more concentrated and do more extractions. Sometimes that may not always be feasible to do if you have limited amount of samples. So now you may pursue a lowering the split in a GCMS. So you may go now to a 10-to-1. But a 10-to-1 now may cause even more challenges. So you may have where the blanks now are not clean. So now it may require more washes in the instruments, more liners more to be changed, to be bought, more costs. So now you have more instrument maintenance and again more costs. So as you can see, it's very, very important that we get a methodology that is as comprehensive as possible. And I'm trying to get to the introduction of the next presentations that talk about what this method might look like. So once again, to stress how important it is that in order for us to have consistency in reporting, if we are already addressing nomenclature, if we address already some of the jurisdictional limitations for reporting by having these different options in NFLIS, by addressing this through our data collection system for the nation, we need to then focus on the detection and identification, because that is the foundation of that reliability and validity of what the data that's being reported. And overall, why is this needed? It is needed because we need to know what are the newest substances out there, how dangerous are they, what kind of studies need to be done so that we understand their potency. That is the overarching struggle that we have when it comes to these drug analysis, and we must overcome it. Because they are hurting people, right? One pill can kill. We're losing lives. There was over 100,000 people that lost their lives last year due to drug poisonings. So we must overcome, and to do that, we need to do it together through collaborations, through network, through having that discussion and sharing data. We can't just talk. We can't just help one lab or another. We need to help collectively and share all the data that we have. And this leads me to what DEA wants to present in this webinar is a global uniform analysis and reporting of drug-related substances. This is it's going to help with consistency for data collection and gathering, and unifies seized drug labs because it can help with having some standardization, as different all the labs are using a very similar method. We have right now this method can do over 400 different chemical compounds in one method. And you are going to hear through the webinar some of the other enhancements that we are working on for this particular method. It enhances investigative and intelligence tools. It can be coupled with algorithms to do prediction and clustering of seized drug exhibits. And all of this leads to enhanced data ingestion into NFLIS for everybody to benefit. All the different jurisdictions, all the different stakeholders to be able to look at a query and see how they do their part for public safety. This is a very fast method. This is a 15 minutes analysis time method. It's very environmentally friendly because it's moving from helium to hydrogen gas, and you're going to hear how to do that in the rest of the presentations. And this particular slide we had done over 300 that were already analyzed. Like I mentioned in the previous one, we already surpassed 400, and we keep increasing as new emerging drugs come in, as new mixtures are brought in. We keep enhancing it so that we can share this information with everybody. Again, this is going to help with the consistency of the data that is being shared, with the capability of that laboratory. It's already been validated not just among DEA laboratories, but we also have partners who are beginning to implement it in their laboratories, such as CBP. We also have some other state laboratories that have already started the implementation of it, and even internationally. So this method, because it's so comprehensive, and it's not a very lengthy method, is an extremely wonderful way to ensure that we're not missing new compounds that are emerging. And like I said, we are constantly updating it as new substances come up. So thank you for your attention and participation in the chat and the QA pod. Like I said, we will address your questions. Our next presentation is development and validation of the GUARDS method at the DEA Special Testing and Research Laboratory, and this is going to be presented by Michael Weaver. Michael, take it away.
Thank you, Agnes. So a brief introduction. My name is Michael Weaver. I work in the Method Development and Technology Transfer Group here at the Special Testing and Research Lab in Knowles, Virginia. We're a small group, but I think it's a privilege to have a group like this that does develop methods and validate them for the rest of our field labs, and we try to work out the kinks and try new things and evaluate new technologies. So I know a lot of forensic labs don't have those resources, so I think it's a very good advantage that we have here. So I'm going to talk about the development and validation of the GUARDS method here at our laboratory. Quick disclaimer that these are my opinions and they do not represent the opinions of the DEA, Department of Justice, or the U.S. federal government. Also, I don't have any financial interest to disclose, nor affiliation with the manufacturer of the analytical equipment described here. So good morning. This presentation is going to cover the history of the GUARDS project, a brief background on the analytical need we were trying to assess, and important milestones and decisions made during the development and optimization of the method. After discussing the genesis of the GUARDS method and its final parameters, we'll dig deeper into some of the specifics of the method validation conducted at our laboratory, including numerous additional evaluations that go beyond our policy requirements. We'll also briefly touch on some of the interlaboratory results obtained within our lab system. This is the first method where not only were we using hydrogen from the beginning, but also evaluating different columns that are more appropriate for hydrogen, such as a narrow bore column. So as you'll see during the presentation, a lot of effort was put into making sure that all the variables were evaluated and taken care of before we locked the method down and moved into the validation phase. Our first topic will cover method development. So a little bit of history. Before 2021, DEA focused on developing new laboratory system standard operating procedures for seized drug analysis with targeted analytical qualitative methods. These methods were tailored to fit existing field instrumentation, i.e. a common column type, which was a 15 meter, 0.25 millimeter, 0.25 micrometer DB5 column. For each GCMS method for the targeted methods, both a helium and hydrogen carrier gas version were developed and validated. There were also 3 targeted methods developed using GCFID for a total of 9 standardized targeted methods. However, a general purpose laboratory system method was still needed. During the development of a standardized general purpose method, an additional challenge was asked of us. Develop a highly selective and efficient method not only for DEA analysts, but a method that could be made available to the general seized drug community. This method could be shared across the forensic community and used by state and local labs throughout the world to standardize reporting requirements to NFLIS. Another requirement was established to develop a GCMS method to use hydrogen as a carrier gas. This requirement also led to being asked to use a narrow bore column, as those are the most appropriate columns when using hydrogen. As part of this larger goal, DEA is also developing a manuscript for publication in a peer-reviewed journal, which is a step in turning GARDs into an ASTM test method and being published on the OSAC registry. In March 2023, our group began method development using a narrow bore 20 meter length column. This column was a DB5 column phase and was optimized on a GCMS equipped with a hydroinert source. The instrument originally had an extractor source, but it was replaced with a hydroinert source prior to any method development work. Method conditions were optimized for this column and had a final runtime of approximately 15 minutes. How did we gauge if a method was fit for purpose? Our group had compiled method limitations of close eluders to separate with this new method. Multiple mixes were made that contained these close eluders, and the method was then refined to separate these critical pairs to greater than 0.1 minute retention time difference, which was our policy at the time. This DB5 column was not able to generate retention time differences greater than 0.1 minute for the halogenated fentanyl analogs in a 15-minute runtime, though it came close to the 0.1 minute threshold. The elution order of compounds remained the same as we'd experienced using the 15-meter column previously employed for our targeted methods. This elution order similarity was due to the same phase ratio of the column. Later, we will revisit elution order and column phase ratio. Finally, during this time, we ordered from the CDC a free fentanyl analog kit containing approximately 250 fentanyl-related standards. Here is an example of our general purpose suitability mix run with the optimized method parameters on the DB5 column. Separation between close eluders, such as phentermine and methamphetamine, seen here about 2.3 minutes, as well as cocaine and tetracaine, here at 8.8 minutes, approach our initial policy threshold of 0.1 minute retention time difference. Dimethylsulfone, seen here at 1.1 minute, was our early eluder, and it was chosen as a marker to gauge whether retention is actually occurring. This marker was used to measure whether elution time exceeded twice the holdup time of the column and method to generate a retention factor greater than 1, i.e. K is greater than 2 times T naught. This criterion also dictated the starting temperature of the following method iterations. Too high of a starting temperature would not result in sufficient retention. On the other hand, trazodone, seen here at 14 minutes, was used as our late eluting compound to mark the ending time of the method. Thus, all of the methods tested had to capture dimethylsulfone through trazodone as an initial test. In the summer of 2023, we obtained a second instrument that was converted to hydrogen from initially being used on helium. Also, our previous standardized GCMS methods used a HP or DB5 column phase. However, since this method was to be deployed beyond our own lab system and based on feedback from querying other laboratory systems outside DEA, the question arose of whether to evaluate other column phases. There were three ultra-inert column phases available in the narrow bore 20-meter size, a DB1, a DB5, and a DB35. We had already evaluated the DB5, so we ordered the DB1 and DB35 columns to also test those. On our converted instrument, that was an older GCMS with an extractor source, a DB1 narrow bore column was installed in it. A method was optimized on this column, which gave a slightly shorter runtime of 14 minutes, but did not prove any more efficient in terms of separating the fentanyl analogs we were trying to separate. Presented here is a tick of the general purpose suitability mix run on the DB1 column under optimized, i.e. programmed oven temperature ramps, and resulting in a runtime of about 14 minutes. Trazodone elutes more than 1 minute earlier than the method that was optimized on the DB5 column, which you can see at 12.9 minutes. An elution order change was noticed with caffeine and eudolone, which was a critical pair we were trying to resolve previously with the DB5 column in the targeted methods. Now caffeine eluted earlier than eudolone. Also, hydrocodone and tetracoxane emerged as a new pair of post-eluters. Separation for this mixture was adequate, but when analyzing the other diagnostic mixtures, it became clear that fentanyl isomers would also not be sufficiently resolved using this particular column phase. Here is a tick of the DB35 column that was optimized with this method. The DB35 column was installed on our initial GCMS, which had the hydroinert source. This column was the most polar of our columns that we tested, which resulted in the longest runtime. Here you can see trazodone at 19 minutes, but it also demonstrated the greatest separation between structurally similar compounds. During method development on this column, retention time shifts and switches, which were not surprising, were noted compared to the other column phases. For instance, caffeine and eudolone that we previously saw, which were a pair of close eluters, were now easily separated by more than half a minute. Meanwhile, other compounds eluted closely, such as tetracoxane and levamisole, which was unexpected because these are not structurally similar. The column phase resulted in 8 elution order changes and a mixture of 18 compounds alone. Then the question arose, when we had compiled all these different methods on different column phases, what would be the most effective way to compare the column phases tested since the elution order changed? The change in this retention time order meant that merely compiling a selectivity spreadsheet would not easily visually depict the resolving power of these columns. With the use of polar plots depicted here, the distance of a vector, a compound of interest, from a central compound could be graphed to show retention time differences. These plots were generated for each of the diagnostic mixtures that were used for method optimization. Here, 3 polar plots are shown displaying the heroin alkaloid mix that was analyzed. Imagine taking a vantage point from the heroin peak in the chromatogram and viewing the other alkaloid peaks and then plotting this distance. The distances to the other compounds from this central point, which is independent of elution order, is graphed here. The larger the distance, the greater the separation, and a repeatable pattern was seen each time a mix was graphed using a polar plot. Red vectors here show compounds eluting after the central compound, while blue vectors represent compounds eluting before the main compound. So in each of the three column phases seen here, noscapine and papaver do elute after heroin. And you can see that the vectors increased as we went towards a larger polarity. This process of plotting retention time differences as vectors was repeated for each diagnostic mixture used for development. In this example, the phenethylamine mixture is plotted across three column phases. This example, interestingly, shows that the early eluting phenethylamines analyzed here did not show a stark separatory preference among the column phases. In other words, there was no obvious advantage. We also ran a cannabinoid mixture and did the same process to analyze its separatory ability versus column phase. As opposed to what we just saw with the early eluting phenethylamines, the later eluting cannabinoids showed a strong separatory preference for the most polar column tested, which was not completely unexpected. One important mandate when we were creating this method was for the identification of fentanyl-related substances. A mixture of orthopara and metafluorofentanyl was analyzed on each column phase, and the results are shown here. Again, the most polar column phase shows a clear advantage in resolving these positional isomers, with the DB35 column demonstrating a greater than 0.1 minute retention time difference between the three isomers. The same process was repeated for orthopara and metafluorofentanyls with a similar conclusion. After analyzing the retention time differences for the various mixtures run on each column phase, a summary was generated highlighting the findings. As expected, method runtimes increased with increasing polarity of the column phase. However, the separatory ability of the DB35 column became apparent when attempting to analyze fentanyl and parafluorofentanyl precursors, 4-ANPP, and despropionyl fluorofentanyl. The only column phase able to separate this pair was the DB35, indicating at least that these similar compounds would be better resolved. And here's an example of that. You can see that they co-elute on the DB1 and DB5 methods tested. In August 2023, we presented the working method, which was about 20 minutes, using the DB35 column for approval to begin validation. The feedback received was that the proposed method selectivity was promising, but the method runtime could be reduced. This mandated a policy change, reducing our initial retention time acceptance criteria from 0.1 minutes to 0.05 minutes. And that was suggested to allow the method to be shortened and account for the narrow peak shapes seen using hydrogen and the narrow bore column. Further work was conducted to reduce the runtime of the method. The 20-meter DB35 column was cut manually to shorter lengths, such as 18 meters, 15, and finally 12 from a starting 20-meter column. This clipped column was then reinstalled, pumped out overnight, retuned, and then had the selectivity mixes that we previously discussed run on each different length, with optimization of the method performed before the next round of trimming. In each instance, clipping the column naturally did result in a shorter runtime. However, the retention time differences also diminished between the compounds, which was expected. Also, the only commercially available column for the narrow bore DB35 column was a 20-meter length, meaning that a shorter column would be a custom order. An interesting internal debate began to arise when attempting to shorten the method runtime using the DB35 column and reducing its 20-meter length via column clipping. Given the more polar phase of the column, would the use of time-defined oven temperature ramps be as necessary as when using a less polar column? In other words, would the innate selectivity advantage of the column type be sufficient to produce acceptable separation without fine-tuning oven ramp temperatures? Here in the top tick, which I realize is a busy slide, but it's just to show the separation of the general mix. It is run on a 15-meter column with no hold times in the top tick. The column is simply heated at its maximum rate through the entire run with a short hold at the maximum allowable temperature at the end. The bottom tick is the same mix, the same general purpose mix, run with an oven ramp hold program. This method is longer at 15.5 minutes versus the no temperature hold program above at 11.8. Here is 2 ticks showing the same general purpose mix using a 12-meter column. In the top tick, you can see that there are no hold times, and the method is even shorter at about 10.5 minutes. The bottom tick is the same mix run with an oven ramp hold program. The method is also necessarily longer at 12.4 minutes. While not unexpected, the difference between the temperature program versus the no temperature program approaches became less significant as the column length decreased, i.e., there was less chromatographic real estate available to demonstrate large retention time differences. During this time, we also went back to the original 20-meter column and started playing with the flow rate to try to reduce the runtime. This tick, which is the same general purpose mixture, demonstrates a 15.2-minute runtime on the commercially available 20-meter DV35 column. Flow rate was increased from 0.8 mils per minute to 1.2 mils per minute during the final 4 minutes of the method. At this point, retention time differences from the diagnostic mixtures had been accumulated for 4 column lengths with various method runtimes. With this data, several candidate methods were presented before beginning validation work. A method using the 12-meter length column with no oven ramp hold times on your left, a method using the 15-meter length column with oven ramp hold times in the middle, and a flow rate revised version of the original 20-meter optimized method. This chart of close eluders shows the general progressive trend in separation with the longer column, with close eluders whose retention time difference is less than 0.05 minutes being highlighted in red. Another way to visualize these differences is shown in this bar graph. While the difference for earlier eluders was not as pronounced, seen in the polar plots that we've already looked at, the retention time differences for larger compounds became more pronounced with column length. While runtimes ranged from 10.9 to 15.2 minutes, the extra runtime in the longer method resulted in larger retention time differences for the fentanyl-related substances, as you can see here with beta-methylfentanyl and fentanyl, and then the ortho, para, meta, fluorofentanyl, and chlorophenols. Ultimately, the final method parameters were chosen using the 20-meter column length. The GUARDS method underwent a total of 96 method variations comprising 3 column phases, 4 column lengths, and tested with 7 custom mixes comprised of 40 close eluders. That was 96 method variations with 7 mixes and approximately 700 injections. With method parameters thoroughly evaluated, method validation can now commence. What about partner input in the seized drug community? During this time frame, OSAC and SWIG drug members were queried as to whether they would be interested in a general purpose method using hydrogen, as well as their current general purpose method parameters and the compounds they use to gauge separation suitability. While some labs are already using hydrogen as a carrier gas, the majority of labs queried did not. Additionally, most labs' general purpose methods were longer than 15 minutes, with some approaching or even exceeding half an hour. Regardless, the DEA incorporates some of the critical pairs they use to test their methods into its method assessment scheme. Thank you to all the partners who responded with their method information and suitability requirements. Now, at the cusp of beginning method validation, one of the devil in the details aspects of the GUARDS project was addressed, the potential drop in sensitivity when using hydrogen. One of the tenets in converting from helium to hydrogen in GCMS was that there would be an expected loss of sensitivity, often threefold or more. After reviewing some hydrogen instruments in our laboratory system that were already using targeted standardized methods, some instruments perform well with tunes that passed regularly. However, there were many instruments which required several tune attempts to produce a passing standard tune, which is a policy requirement for our laboratory system. Furthermore, the failing tunes using hydrogen often displayed greater than 200 peaks and a poor 503 mass overcharged peak shape, which, when using a helium instrument, would indicate a dirty source. However, source cleaning made no difference in reducing peaks or otherwise improving the tune when using hydrogen. During the initial method validation, auto-tune was tested to see if the sensitivity of the instrument could be improved. Auto-tune generated passing tunes with every attempt and approximately a 20 times higher response than standard tune. E-tune, an extractor source tune, was also tested and provided an even higher response. Unfortunately, auto-tune would not preserve the ion ratios that standard tune enforces. The problem with having changeable ion ratios would be matching to standard libraries and comparing instrument to instrument. Comparing A-tune and E-tune tune reports show that in each case the repeller was maximized to approximately 40 electron volts. Using standard tune, the default is set to 20 electron volts. When setting the repeller voltage higher on standard tune, the resulting tune passed easily and showed higher sensitivity on the resulting total ion chromatograms. More in-depth information on tune optimization will be presented later in this webinar when helium to hydrogen conversion is discussed more in depth. With the standard tune parameters optimized, validation continued on the hydroinert GCMS using a general purpose mixture that contained 13 compounds that we've already seen. Meanwhile, validation began on the older GCMS with the same general purpose mixture, as well as a mix of halogenated fentanyls and a mix of derivatized amphetamine and methamphetamine. While validation was ongoing, the fentanyl analogs ordered earlier from the CDC were added to selectivity for the method. By late November 2023, validation was completed for both instruments. Inter-laboratory reproducibility testing was completed at 2 DEA regional laboratories, and the method was deemed fit for purpose in the DEA lab system. As part of the original challenge in developing a general purpose method, the idea of estimated drug purities using the method was introduced. The need for a way to measure drug purity trends became clearer. One instance where this data could be valuable would be in standardizing how state and local labs report to NFLIS. This method was also suggested as a standardized method in response to the TRINC Act that Agnes previously discussed. So how would your lab be able to implement the GUARDS method? The GUARDS method was designed to be an easy method to adopt. While we used Agilent instrumentation, there's no obstacle in implementing the method on another manufacturer's GCMS system. Here, both an Agilent 7890B GC coupled with a 5977A mass spec and an Agilent 8890 coupled with a 5977B mass spec were used for validation. The column type and dimensions are a DB35 ultra-inert column, 20 meter length, 0.18 millimeter internal diameter, and 0.18 micrometer film thickness. The biggest hurdle some might face to implement GUARDS will be the transition to using hydrogen as a carrier gas. There will be more information presented later on this process from my colleague, Charlie Mitchell. Supplying hydrogen to the GCMS can originate from one of two sources, gas cylinders, or much more preferably, hydrogen generator. Otherwise, GUARDS is a regular GCMS method in terms of sample preparation and analysis. Most solvent systems are suitable for analysis with the caveat that chlorinated solvents have the potential to interact with hydrogen over time. Here you can see the validated GCMS method parameters. Due to the column's higher phenyl content of 35%, the temperature can be held higher than a DB5 column. for those that may have their pulses raised by the 340 degrees Celsius hold time. These parameters are also publicly available at the URL listed below. What are some limitations of the GUARDS method? The base GUARDS method will not detect compounds luting after 15.2 minutes, such as sildenafil and related compounds. Samples suspected of containing these compounds should be analyzed using an extended final hold time. An analysis of 39 nitazene compounds showed that 30 of these compounds eluted within the 15.2-minute standard runtime, with some N-pyrrolidino and N-piperidino nitazene compounds requiring an extended hold time of 2 minutes, so a total runtime of 17.2 minutes. Noscapine shows signs of breakdown due to a combination of its late elution time and the high oven temperature. Also, PCP and its thiophene analog, TCP, as well as xylazine and propane co-elute using the GUARDS method. Additional co-eluting compounds are 9S, delta 6A, 10A THC, and delta 8 THC. Hence, a targeted cannabinoid-specific method is recommended for these compounds. What are some of the advantages of the method? Because it does use hydrogen as a carrier gas, you do not need helium or helium tanks, which can be expensive and hard to acquire. And because it uses hydrogen, which is half as viscous as helium, it allows faster chromatography with often better selectivity. This speed allows the use of this midpolar column, which would not often be a candidate for a general purpose method due to its longer runtime when using helium. Displayed here are the most often identified controlled substances in the DEA lab system through the first 9 months of fiscal year 2024. Notably, each compound is well resolved from one another. In summary, efficient separation is achieved in a time-efficient 15.2 minutes. Next, we're going to talk about the details of our method validation process. The International Standard 17025-2017 states that the laboratory shall verify it can properly perform methods, ensuring that it can achieve the required performance. It also states the laboratory shall validate non-standard methods, laboratory developed methods, and standard methods used outside their intended scope are otherwise modified. Also, in conformance to ASTM E3255, method validation is required to demonstrate that methods are suitable for their intended purpose. Labs adopting methods validated elsewhere, like the GUARDS method, shall verify the validity and reliability of those methods. Why do we perform method validation? To provide objective evidence that the methods used are reliable and fit for purpose. It gives the laboratory, its employees, and its customers a greater confidence in the results. And it provides analysts knowledge of the practical details of performing the method, including awareness of any critical steps in the process. It also assesses the strengths and limitations of the method and allows the analyst to make an informed decision regarding an appropriate analytical scheme that results in reliable and scientifically supported identifications. The next few slides will illustrate how the GUARDS method has successfully undergone method validation. Each of our methods used in the lab system undergo a validation process. For the GUARDS method discussed today, these methods underwent qualitative method validation. This process involves 4 components: selectivity, ensuring that compounds of interest do not co-elute; repeatability, which is short-term precision testing within 1 day; within lab reproducibility, which is retention time precision, typically over 6 weeks; and finally, inter-laboratory reproducibility, where at least 2 other labs must demonstrate that the method performs within policy-defined specifications. An important reminder for validation documents is that they are living documents. For example, when new compounds are analyzed, their retention times are added to our selectivity spreadsheet. The seized drug landscape of compounds is ever evolving, so a vigilance for updating validation documents is important to document any limitations that may occur with the method. As mentioned previously, DEA validated the GUARDS method on two different GCMSs. The first instrument was initially equipped with the extractor source that was replaced with a hydroinert source late in 2022. Spectral fidelity was assessed for compounds discussed previously in the general purpose mix by comparing their spectra obtained with the previously installed extractor source with spectra obtained using the hydroinert source. This first instrument had always been used with hydrogen as a carrier gas. The second GCMS is an older instrument with an extractor source. This system was converted from helium to hydrogen after changing the tubing to stainless steel and following Agilent bake-out procedures. Again, more information on conversion to hydrogen will be discussed later in this webinar. This simultaneous validation on slightly different instrumental configurations allowed not only the assessment of sensitivity between the instruments, but also would provide information on intra-lab reproducibility. How would the GUARDS method perform once transferred to another instrument? Here is a tick of the general purpose mixture that was used for initial selectivity as well as repeatability and reproducibility testing. This mix contains 13 compounds with 4 critical pairs each. Each compound was 1 mg per mil concentration except for fentanyl, which was at 0.05 milligrams per mil. For this particular solution, the compounds were base extracted into ethyl acetate. Phentermine and methamphetamine, constitutional isomers, were monitored to ensure that their separation would be sufficient for identification since their mass spectra would be similar. Also, the low-level fentanyl marker was added to make sure that it could be separated and also detected with a signal-to-noise level greater than 3. With validation commencing on 2 instruments with 2 different mass spectrometer sources, a comparison could be made to measure sensitivity between the hydroinert source, here seen in the top tick, instrument 1, compared with the extractor source on the bottom tick, instrument 2. If you look at the Y scale, these data show that the abundances are greater than 2 using the hydroinert source. A mixture was also prepared with the ortho, meta, and para isomers of fluoro and chlorophenol. This mixture was used as a diagnostic mixture as well as to gauge separatory ability of the method. This tick also includes bromophenol analogs. This mixture was not prepared uniformly at 1 mg per mil. Instead, each isomer concentration was slightly varied to ensure that it could be chromatographically identified, aside from running the individual standards, which we also did. In this case, parafluorophenol, parachlorophenol, and orthobromophenol were prepared about 1.25 mg per mil to easily distinguish the largest response isomer. Each isomer, as you can see, is separated by greater than 0.075 minutes. In addition to data corresponding to the general mixture, data was collected for several other mixtures and individual compounds. One mixture containing MTPA, derivatized amphetamine and methamphetamine was also tested in order to demonstrate the method's ability to separate the enantiomers of amphetamine and methamphetamine after derivatization. The derivatized phenethylamine mixture, seen here, and the fluoro and chloropositional isomers of fentanyl mixture were evaluated during validation not only for the purpose of selectivity, but also during the repeatability and reproducibility testing. CDC phenyl analog screening kits obtained from Cayman Chemical were also added to selectivity as method validation continued. As mentioned earlier, some issues with the tuning parameters were encountered during the validation process. Originally, some preliminary repeatability data was collected using both regular standard tune and auto-tune conditions. After meetings with Agilent and optimization of the repeller and standard tune conditions, the repeatability evaluation was repeated. Repeatability tests were also conducted using the mixes in the older GCMS instrument. One important detail worth mentioning here is that when repeatability testing was done, solvent blanks were also tested after each one of the mixed solutions. This data helps to demonstrate that at least during validation, there was no significant carryover observed from sample to sample. Some additional repeatability evaluations were performed. In one set of experiments, early and late eluders were evaluated at high and low concentrations. On another set of experiments, the retention time differences between selected sets of critical pairs were monitored, and we will look at those next. These are the results obtained for the first of these evaluations. When 10 injections of low-level dimethylsulfone and high-concentration dimethylsulfone levels were tested, the difference between the average retention times was relatively low and below the 0.05 separation criteria. An even smaller difference was observed when testing low and high concentrations of fentanyl, with a retention time difference of 0.008 minutes. These results indicate that even when there are significant differences, greater than 30 times, in concentration levels, the retention times observed when using guards are not significantly affected. This is likely due to the clean and sharp peak shapes observed with this method. In addition to the routine retention time repeatability evaluation, an evaluation was also conducted on how the retention time difference, delta RT, between close eluting peaks was affected over 60 injections, which was 30 sample mixes and 30 negative controls. As described before, there are multiple critical pairs to choose from, 4 pairs in the general mix, 2 pairs in the derivatized methamphetamine-amphetamine mix, and 4 pairs in the halogenated phenols mix. The table shown here illustrates the retention time and delta retention time of results obtained for the phentermine methamphetamine critical pair. And as you can see, the delta retention time values remain very constant across the duration of the repeatability evaluation. Another way of illustrating these results is using box plots, such as the one included here for the tetracaine-cocaine critical pair. The box plot on the left shows the dispersion of delta retention time values. The red plus sign represents the average delta retention time, and the green rectangle covers the range between the 25th and 75th percentile of the data. The outer lines are the whiskers, illustrate the minimum and maximum data values. As you can easily see, delta retention time values did not significantly change across the repeatability testing window. On the right, you can see 2 plots representing the dispersion of retention time for tetracaine and cocaine. You can easily observe that the differences are significant with 0 overlapping values. And if you're wondering about the critical pairs for the other 2 mixtures, here you can see some of their results. On the left, you see the delta retention time values between the L and D methamphetamine, and on the right, those recorded when monitoring para and orthofluorofentanyl. Not only are these retention time differences above our internal policy-mandated acceptance criterion of 0.05 minutes, they are demonstrated to be highly repeatable. What about the evaluation of long-term precision or intra-lab reproducibility? This testing covers a 6-week period to allow for a positive control analyzed within 1 month to be used to comparison for sample analysis. Routine procedures were completed using the 3 suitability mixtures, and not only were absolute retention times reproducible, but also the delta retention time values monitored for all the critical pairs. Here you can see the results collected during week 0, which is baseline and the repeatability assessment, and the following 5 weeks of analyses for C24 and levamisole, L-methamphetamine and D-methamphetamine that were derivatized, and para and orthofluorofentanyl. The evaluation of the retention time acceptance criterion of 0.05 minutes was also included. The data here illustrates some partial reproducibility results for the general purpose mixture. For each of the compounds evaluated, the average standard deviation 2 times the standard deviation and 3 times the standard deviation were calculated, and then the maximum values were identified. Those maximum values are illustrated in bold here for the new GCMS with the hydroinert source, and also for the older GCMS where the methamphetamine, amphetamine, and fentanyl mixtures were also tested. As you can see, the 0.05 minute criterion selected approximately represents a 95% confidence interval. When the interlab reproducibility testing was completed, an evaluation of their data was also completed. As you can see here, the results fit nicely within the 0.05 minute retention time criteria. And this is another lab's data, which is even tighter, with 0.02 being 99% confidence interval. A short summary of the validation process that guards underwent is outlined here. At our lab, the method parameters were finalized, tested for precision, both short-term and intermediate, while selectivity testing was also conducted. Upon completion of our lab's work in November 2023, the method was then transferred to 2 other DEA laboratories where the same process was performed to assess whether the method meets our policy specifications. This interlab reproducibility testing was completed in February 2024, and the method report and validation packet were posted internally in March 2024. At that point, all DEA laboratories could begin their own verification process of the guards method. Here, in a short preview of the next presentation, is a stack kick showing the retention time agreement between 4 DEA laboratory systems across the country. And as you can see, the retention times are very close to one another across 5 laboratories, 4 others, including our own. I want to thank everyone for your time, and now we're going to have a short break.
Welcome back from our morning break. We are going to continue with Mark Fridge's presentation, implementation of the guards method throughout the DEA laboratory system. Mark, take it away.
Okay. Good morning and welcome back from that short break. Thank you, Mike Weaver, for that presentation on the development of the guards method. This presentation will provide an overview of the guards method implemented throughout the DEA lab system through an interlaboratory study. The main objectives of this presentation, as Mike mentioned in his presentation, the guards method developed by the Method Development and Technical Transfer Group at the Special Testing and Research Laboratory was designed to offer a GCMS method that allows for the standardization analysis of both commonly encountered drugs as well as new and emerging compounds such as the various inosine compounds recently seen not only within the DEA laboratory system, but also in state and local laboratories. This presentation will discuss an interlaboratory study which involved the analysis of 3 sets of solutions. The goal was to see if we could extend the capabilities of the guards method to not only separate and identify over 400 compounds to date, but also determine if there was a way this method could also produce an estimated purity. The presentation's agenda will be, first, I will describe how the sample solutions were made and distributed. I will then show how the data was analyzed. I will go over how the method was evaluated across many instruments throughout the DEA by looking at the various compounds retention times. I will then go through the data analysis to evaluate the possibilities of estimating purity levels. Basically, I looked at the area counts of the compounds versus the internal standard marker area count, and then determined a correction factor. At the Special Testing and Research Laboratory, we prepared 3 stock solutions using octocosane or C28 as an internal standard marker. A stock solution was paired with 9:1 chloroform to methanol with C28 at 0.05 milligrams per milliliter. This represented a 1% marker. The first solution contained a fentanyl at a low level, cocaine, trazodone, tetramythol, and caffeine. The second solution contained fentanyl at a higher level, parafluorofentanyl, heroin, noscapine, and acetaminophen. The third solution contained dimethylsulfone, methamphetamine, MDMA, ketamine, and phentermine. This solution was base extracted with 2-normal sodium hydroxide. The fentanyl was prepared at 2 different concentration levels. The levels that we picked, the low level was 2%, which was to mimic purity levels typically seen in tablets, and the higher one was at 20% to represent purity levels seen with powders. This is a table of the 3 solutions that I just mentioned. Solution 1 on the left in the black, solution 2 in the green, and solution 3 in the blue. As previously mentioned, C28 is the internal standard marker, and it was added at the 1% level, which corresponds to 0.05 milligrams per milliliter. You can see the various levels of the other compounds. The purity ranges from 2% from the low fentanyl to 40% for cocaine and acetaminophen, and the other compounds were either at the 10 to 20% purity levels. After the solutions were made, a portion from each of the 3 mixes, along with the internal standard solution, were placed in vials and mailed to the different DEA laboratories. The labs were instructed to refrigerate the solutions upon receipt until they were going to be used for analysis. Each mix was to be analyzed 10 times with a blank in between each injection for a total of 60 injections per instrument. The solution mixes were to be distributed in 10 different vials rather than 10 injections from just 1 vial. If labs were going to use multiple instruments, they were instructed to recap the vials prior to putting them on another instrument. For the entire interlaboratory study, 9 DEA labs submitted data. Of those 9 labs, data was collected on 21 different instruments. 1 lab from Maryland, the Mid-Atlantic Laboratory, actually used 7 different instruments. All of this data meant each of the compounds had a total of 210 raw spectra collected. Once all the data was collected, the labs were then instructed to upload all of the raw data to one central shared folder, which I then transferred to one GCMS, where all the data was reviewed and processed. The interlaboratory study of the GARDS method provided excellent retention time precision. This was demonstrated within day by the repeatability evaluations through the method validation and verification process, along with the interlaboratory study. The retention time precision was also demonstrated between days by the reproducibility evaluations, also from the validation and verification of the method, along with the interlaboratory study. Finally, the excellent retention time precision of the GARDS method was demonstrated between instruments. As mentioned earlier, one DEA lab had it on 7 instruments at the time of the study, and through the interlaboratory study, 21 different instruments were evaluated. This is a chart of the retention times collected for each of the compounds in the laboratory study. Each of the compounds are in a different color, and the y-axis is the retention time in minutes. The compounds are ranged from the earliest eluter, dimethylsulfone, to the latest eluter, trazodone. The box plots represent the range of retention times for all of the data collected from all of the laboratories. Again, each compound was run on the GARDS method 210 times. The box itself represents the first and third quartile, or the 25 to 75% range of the retention times. The ticks above and below the boxes indicate the maximum and minimum times, and any spheres you might see represent outliers. You can see for the most of the compounds, the maximum and minimum times are very close to the first and third quartile levels, with very few indicated as outliers. You can also see the gray and blue boxes, which are the left 2 ones in the area where there are 4 boxes in a row, are almost the exact same. These are the 2 different purity levels for fentanyl. Another way to illustrate the excellent retention time precision is to look at the standard deviations of the retention times for each compound. The standard deviations range from 0.053 to 0.17. As shown in the previous chart with the two fentanyl purities, standard deviations for the low and high fentanyl are both about 0.16. You can also see how robust this method is by looking at the retention time of the internal standard, C28, over all the instruments and within each mix. The chart on the left illustrates the retention time of C28 for each of the mixes. Once again, the box plots show the first and third quartile, along with the minimum and maximum retention times collected. There were no outliers. The table on the right is the statistical data for all 630 injections collected in the laboratory study for C28. You can see how close each of the statistical values are from the first quartile to the median to the third quartile and the mean. The average retention time mixes for 1 through 3 were 8.861, 8.860, and 8.858 minutes, which gives us an average across the board of 8.860 minutes and a standard deviation of 0.087. The next thing I looked at was to see if we could determine an estimated purity based on the GCMS data. After gathering all the data, we looked at the area counts. The image on the left shows a printout of a GCMS chromatogram from one of the sample solution injections. On the top is a table for each compound integrated, and in yellow, I highlighted the area counts for each compound. I calculated the relative levels for each compound. This is where I took the area of each peak and divided it by the area of the internal standard. Analyzing all of the raw data illustrated the varying responses observed for the compounds and hence the associated relative levels. The table on the left shows the average retention time, peak area, and relative level for all the compounds that were analyzed in the interlaboratory study. A few things to note from looking at the data. First, look at the yellow highlighted values. These are the two levels of fentanyl. The low was 2%, while the high was 20% for a 10 times difference. However, when you look at the average peak areas and hence the relative levels themselves, there is about an 18-fold difference. The chart on the right shows the average peak areas for the various compound percentages. Once again, the percentages are based on the 1% internal standard marker, C28. This shows that even compounds prepared at the same levels still have fluctuation in the peak areas. This can be observed by looking at the bar for each of the 20% compounds, which are basically in the middle of that chart, and also looking at the last two on the right where the compounds are at 40%. This table illustrates the comprehensive data collected in the interlaboratory study. It shows all of the relative levels for all 21 instruments. Each number under the compound listed at the top are the averages for the 10 injections on the respective instrument. You can see how they vary by instrument. It can be best observed by looking at the standard deviations and the relative standard deviations. The standard deviation ranges from 0.19 to 8.13, and the RSD ranges from about 19% to 186%. But removing noscapine as an outlier, since it doesn't appear to chromatogram well from instrument using the GARDS method, the RSDs now range from 19% to about 60%. This bar chart is another way to visualize all of the data from the table on the previous slide. It illustrates the minimum, median, and maximum relative levels for each compound. Once again, you can see that the compounds that were added at the same level behave differently, which should not be shocking when you recall the average peak areas also did not behave the same for compounds prepared at the same purity levels. After analyzing all of the data and determining the relative levels for each compound based on the peak areas against the peak area of the internal standard, the next thing I looked at was what we called the correction factor. The correction factor is the number the relative level needs to be multiplied by to obtain the compound's actual purity level. To determine the compound's correction factor, first we determined the relative level. Next, we took the purity level of the compound and divided it by the relative level to give us the correction factor. Theoretically, if you did not know the purity of the compound, unlike in the laboratory study, you could get an estimated purity by multiplying the relative level of the compound you have in your sample by the correction factor. This table looks very similar to one I previously showed a couple slides ago that showed the relative levels for each compound for the 21 instruments. This one now illustrates all of the calculated correction factors. Once again, each number under the compounds at the top is the average of all 10 injections for that compound on that respective instrument. The standard deviations here range from 0.21 to 6.86. Noscapine, once again, is not surprisingly highest since it does not chronogram well, and the RSDs range from about 15% to 37%. This chart illustrates the box plots of the correction factors for each compound. The range of the correction factors for the majority of the compounds range from about 1.5 to 2.7 for the first and third quartiles. From the data on the table from the previous slide, the box plot for noscapine further illustrates how it was the outlier compound compared to the other compounds in this study. If we want to select a second outlier, it would be dimethylsulfone, the box plot to the right of noscapine. The next step was to see if the correction factor was more instrument dependent rather than one universal correction factor that could be used to give an estimated purity. The initial work was to use 2 instruments at the Special Testing Research Laboratory over a period of time. And through testing, could we tell how long a unique correction factor for a particular instrument is good for? I'm in the process of collecting data to determine this. I made a solution similar to those for the interlaboratory study, but this time I only included cocaine, heroin, and fentanyl, along with the internal standard. I'm currently collecting data to determine how long correction factor is good, meaning how long will provide a reasonable estimated purity. I'm doing this in a 3-step process. First, I'm in the process of performing a 6-week study where the solutions will be injected once a week. The first week I had diluted the stock solution 9 times, which would give me a total of 10 concentrations. Subsequent weeks, I did 4 different dilutions. Second, I wanted to see within-day results. I did a morning, then an afternoon series of injections to observe any changes. Finally, I plan to collect data daily for an entire week, each day from Monday to Friday. The first and third steps are still ongoing. The graph on the left shows the correction factors for all 3 drugs, cocaine, heroin, and fentanyl. From the first week of data collection, where there was the series of 9 dilutions from the stock, each point is the average of 3 consecutive injections for the 10 concentrations. Taking into consideration the entire purity range, the table shows that once you get around 30-ish%, the correction factor stays relatively the same or more linear as compared to the full range of dilutions. The chart on the right shows the relative levels for the 3 compounds at the 10 concentrations. Dilutions range from about 10% to 100% based on the internal standard, C28. All of the R-squared values for the linear trend line are greater than 0.99. As mentioned previously, following the week 1 series of dilutions where I had a total of 10 different concentrations run in triplicate, I then ran 4 dilutions in triplicate for the additional weeks. The purities for each of the compounds were 10, 30, 50, and 70%. This table shows the multi-week data collection of the 4 different dilutions on one instrument. The correction factor for cocaine ranges from 1.72 to 2.32, with a standard deviation range of 0.07 to 0.28, and RSD from about 4 to 10%. Comparison from the intra-laboratory study on multiple instruments, the correction factor was 1.53 and had standard deviation of 0.38 and an RSD of 27.7. The correction factor for heroin ranges from 2.09 to 3.11 with standard deviation range of 0.05 to 0.3 and RSD ranging from 2.4 to about 9.7. Comparison from the intra-laboratory study, the correction factor was 1.68, standard deviation 0.37, and RSD of 22.1. Finally, the fentanyl correction factor ranged from 1.61 to 2.2, standard deviation ranged from 0.04 to 0.23, with an RSD from 2.76 to 10.3. From the intra-laboratory study, we got 2.61 for the lower purity and 1.16 for the higher purity level, and the standard deviations were 0.71 and 0.21 for the high, with the RSDs about 27.3% and 37.2%. The lower standard deviations and RSDs when only looking at data from one instrument are lower than when we analyze all the data from the digital laboratory study and tried to see if there could be a universal correction factor. Initial data collected on the instrument-specific correction factor study to determine an estimated purity using the GARDS method seemed promising looking at the initial results as compared to the intra-laboratory study data together. However, there's still more to do and other factors to investigate, such as, how much does the correction factor vary per compound? How often does the correction factor need to be updated per instrument? How does any major or minor instrument maintenance affect the correction factor? And if one correction factor is used, how close to the actual value will the estimated purity be? And what will the uncertainty with that calculated purity be? Thank you for your time and attention, and I will now turn this over to Charlie Mitchell.
Thank you, Mark, for such an informative presentation. Our next presentation will be Transitioning from Helium to Hydrogen as GCMS Carrier Gas, the DEA Experience by Charlie Mitchell. Charlie, take it away.
So, I'm a chemist here at the DEA Special Testing and Research Laboratory. I work a lot with the instrumentation here at the lab. So when our team that was developing GARDS needed an additional GCMS using hydrogen, I was the one to convert that from helium. So today I'll be talking about my experience doing that and hopefully give you some more tips to keep in mind to make your process go a little bit smoother than ours was. A quick disclaimer as well. I just wanted to say that these opinions expressed during this presentation are just that. They're my opinions and they do not represent the opinions of DEA, DOJ, or the federal government. And we have no affiliation with the manufacturers presented in this presentation or any of the equipment described here. So first of all, hydrogen is not new to the DEA lab system. We've been using it since the 1990s. Primarily using hydrogen generators for our GCFID instruments. So in most of our lab systems, we have them attached to an auto refill system with deionized water to make the use of hydrogen gas effortless. You can also attach multiple instruments to one generator, so it makes it very easy. And with the recent difficulty and expense of obtaining helium, we took to using hydrogen gas because of that roadblock. I think even when we order gas around here, we sometimes get a helium surcharge just for ordering helium. So using hydrogen was cost effective for us. The first DEA standardized method using GCMS and hydrogen gas was validated in 2020. And since then, we've done a couple other methods that we've developed. So when using hydrogen gas, the immediately concern that most chemists think of is its flammability. This risk is significantly mitigated by the use of generators. They have a lower reservoir of hydrogen, they have a lower flow, and these generators are often equipped with standby modes and a lot of safety shutdown modes. They're also very robust. In our lab, we have a couple different brands of generators, and our oldest one has one on and off button, so they're very robust. And once your instrument is flowing with hydrogen, it's a good idea to check after installation for leaks of hydrogen gas. And then finally, on your GCMS, if you do have a black cover, some of the companies do have that, so you want to remove it because that's a place where hydrogen gas, if there's a leak, can build. Another concern when using hydrogen is going to be the chromatographic concerns. So often with hydrogen gas, you see a lower response of the analytes. It's usually 2 to 5 times lower, tailing of peaks. And because hydrogen is not inert like helium, there's a possible of chemical rather than electron impact ionization. And we'll talk about how we can mitigate these concerns in this presentation. So before moving on, we want to talk about the advantages of using hydrogen gas. So we want to first, I'll say one more time about the generators, how easy they are to use and obtain, and they can run off water and be set up to an auto refill system to make it very simple, and there's very maintenance with them. They're more convenient and cheap rather than using the helium tanks. Another advantage to using hydrogen is the viscosity is about half of helium. So this allows our analyte to elute faster through the column. On this Van Dietmer plot below, it shows that hydrogen offers more chromatographic efficiency as the flow rate increases. So this will give us better selectivity. So let's talk about actually converting your instrument. So either when you have a new installed instrument or one that you're changing from helium to hydrogen, there's a couple physical changes that we want to make. The first tip is just to be patient, which I know can be hard for someone, including myself. So while hydrogen can produce excellent chromatography and response, the transition between the carrier gases can require time. Hydrogen is not inert, so it doesn't behave as quickly as helium. We've set up our instruments and had to let them sit for up to a week to let them settle. So the first tip that you'll want to do when converting or purchasing a new instrument is to use stainless steel tubing and fittings for all the hydrogen lines. Hydrogen can slowly corrode the interior of copper lines, and this results in breakage and contamination. You can also attach a hydrogen filter in between the line to further ensure the carrier gas flowing is pure. Secondly, when helium instruments come, they usually have in the source the 3mm draw-out plate, which is the picture on the left. So you'll want to change that out to a 9mm draw-out plate for hydrogen. And we do this because the larger diameter allows the hydrogen to be removed quicker from the ion chamber to reduce the chances of chemical ionization. The less chemical ionization that occurs, the more spectra collected will resemble helium collected spectra. And thirdly, the flow rate is important in limiting the amount of hydrogen introduced into the source. The higher the flow rate, the larger the chance of chemical ionization occurring, and so recommended flow rates for hydrogen are usually 1.5 mils per minute or less. And this can also result in choosing a narrower column or performing method development. Other changes that we'll want to take into consideration is after the instrument is plumbed and running hydrogen, you'll want to heat the source to a high temperature or baking out the source. This is imperative to optimizing the performance of the mass spec. So you'll want to set the source to its maximum temperature, reduce the EMV volts, and leave the filament on. Set this and walk away, and this is where the patience comes into play. We've baked ours for as long as a weekend, and we've even periodically set it to bake even more as we troubleshoot other issues. The progress of baking out can be monitored by the reduction in tailing and chromatography, as well as the number of peaks detected during the tune process. Further suggestions include using auto-tune rather than standard tune when using hydrogen if that's possible in your lab system. Or you can install a hydroinert source, and this will help compensate for the reduced sensitivity when using hydrogen versus helium. So if you don't follow these physical changes to your instrument, you may end up with a tune seen on the left side. And so on the left, we have a tune that was done when our instrument still had copper tubing, the 3mm extraction lens. You can see we have non-Gaussian peak shapes, a splitting 503 peak, inconsistent peak widths, and a peak count well over 200. Whereas on the right, after we added all of those changes, after about a week of letting it sit, we had beautiful Gaussian peaks, consistent peak width, and a peak count almost under 100. So there were big differences after doing those physical changes. So one of the tenets in converting from helium to hydrogen in GCMS is that there's a loss of sensitivity. This can be up to 3 times a loss. So some hydrogen instruments in our lab system had tunes that were passing and they had no issues, whereas other ones we had failing tunes and we would take repeated times tuning to try to get one to pass. And so after talking with Agilent, we saw that some of the labs were using a repeller ramp and others were not. And so that is something that we will discuss in a bit. Another thing that we looked at when developing the GARDS method is using auto-tune versus e-tune. So auto-tune was tested and it generated passing tunes with every attempt and a 20-time higher response. E-tune also was tested and provided a higher response. Unfortunately, we can't use auto-tune due to our policy because it does not preserve ion ratios that standard tune enforces, and the problem with having changeable ion ratios is matching to standard libraries and comparing instrument to instrument. Another thing with A-tune and E-tune is that the repeller was maximized to about 40 eV, and using standard tune, the default is 20 eV. So when you set the repeller voltage higher on S-tune, this resulted in passing tunes and ticks having higher sensitivity. So looking at the tune reports across the lab system, this is where we saw the difference between the repeller voltages. So our group here, MDTT, invited Agilent and we discussed many problems with hydrogen instruments and how to resolve them. And one of them was the use of the Tune Wizard to use S-tune and have the repeller ramp above 20. So on our top slide here, you can see a tune that is one that we would see a lot before a lot of these changes were implemented. The peak shapes are not even close to Gaussian, lots of splitting. Our repeller voltage is set to under 20 and our E-volts is about 1400. When we allowed the repeller to ramp up to 42, our EM volts went down, our peak shapes became Gaussian, and they no longer split. So this would pass our criteria. And the peak count for before the repeller ramp was above 200, and it was well below 100 for after repeller ramped. And so with our instruments, we would usually tune per our policy once a month or once after any major maintenance is done. Here is a solution that was ran after the repeller has been ramped. So in the red, we have the solution that was ran with the 20 defaulted after the tune, and once the repeller was ramped to higher than 20, it produced the black line and the blue line. So you can see there was a big increase of the response. Another change that you can make to your instrument is including a hydroinert source. And so this is identical to a regular source, except it has the inert rainbow colored coating. So this source, we found that it did improve sensitivity in the instrument that was converted. It essentially changed a low responding instrument into a more reliable one. These sources are either already installed in new instruments that you can buy, or you can get a replacement kit and convert your instrument into one with a hydroinert source. Hydrogen's reactivity has an advantage here. The reactivity of the gas limits the amount of material deposited into the source body, so the source does not have to be cleaned as regularly as helium, if at all. And due to the inert material, you won't want to abrasively clean these either. So after using the hydroinert source, we saw that the response was basically double. So we have the same solution that was run on the same instrument. The only difference is that the source was changed from the old source with the 9mm draw out lens to the hydroinert source. So you can see almost double the response. So an overview of the hardware and software changes you want to do is to use the stainless steel tubing, hydrogen generator plumbed to an auto refill system if that is available to you. Use a 9mm draw out extractor lens or a hydroinert source, or both. You'll also want to, if you cannot use auto tune or e-tune, do the repeller ramp on your standard tune and install a narrower column with a lower flow. And the advantages of using hydrogen as a carrier gas is it includes faster chromatography and higher selectivity over a larger range of flow rates. And so again, we have that picture of the data that was collected of being able to separate the isomers of fluoro, chloro, and bromophentanol, and this was the use of hydrogen gas supported by all of these hardware changes. And those are some references that I found helpful when troubleshooting the instrumentation here. And now we can pass it off to Andrew at CBP. Thank you.
Thank you, Charlie. Our next presentation will be the adoption and implementation of the GUARDS method by CBP Laboratories and Scientific Services by Andrew Moore. Andrew?
Okay. Good afternoon. My name is Andrew Moore. I'm a senior chemist at Interdict Science Center. I've been working here for about 7 years. We're a part of U.S. Customs and Border Protection, Laboratories and Scientific Services, or LSS. In this presentation, I'll discuss the adoption and implementation of the GUARDS method by CBP LSS. I'm going to take a quick minute to briefly explain what CBP LSS is. LSS started in 1848 with the Tariff Act. That's where pharmacists and physicians were hired to work on customs appraisal teams. The first customs laboratory was established in 1892 in Philadelphia, Pennsylvania. So then in 1936, 9 regional customs labs were reorganized under a headquarters division of Laboratories and Scientific Services. Now, LSS has several laboratories located throughout the United States, with analysts for latent prints, digital forensics, canine training aids, pollen, metals and steel, non-human DNA, raw sugar, food, textiles, petroleum, and suspected controlled substances. Additionally, LSS's scope of work include forensic analysis for law enforcement purposes. So we have 24/7 narcotics and radiological and nuclear reachback services, rapid technology assessments of technologies to support our CBP Office of Field Operations. Our laboratories generally fall into 2 categories. First, the field labs that are fully accredited to provide confirmatory results to the customers in the respective areas of responsibility. There are also forward operating laboratories. These are typically smaller than the field labs because the analysts are stationed alongside the officers and agents at field locations. That includes ports of entries at airports, land borders, seaports, and express consignment facilities. The co-location of analysts and officers allows for rapid presumptive results. So that's a very brief overview of LSS. So I'll continue with the adoption and implementing of the GUARDS method. I also have a couple of disclaimers to read. First, I have no commercial or financial interest to disclose as part of this presentation. and the views expressed in this presentation are mine and do not represent the official policy or position of the Department of Homeland Security and U.S. and Customs and Border Protection. Okay, so over the past several years, the availability of helium has preceded several labs change their GCMS carrier gases from helium to hydrogen. As more GCMS methods were being created and used, LSS wanted to standardize their methods, so they began working on possible ways to accomplish that. Jump to April of 2024, when CBP attended a brown bag colloquium where DEA presented the GUARDS method. We learned that GUARDS was an acronym for Global Uniform Analysis and Reporting of Drug-Related Substances. We also learned that as a general purpose method developed by DEA for the qualitative analysis and identification of controlled and non-controlled substances. We were shown that GUARDS was suited for the qualitative analysis and identification of the positional isomers of fluorofentanyl and chloropentanyl, as well as the diastereoisomers of amphetamine and methamphetamine. We saw that GUARDS method had a runtime of 15.2 minutes, and that compounds eluting later than that could be analyzed by extending the final hold time. After this presentation, we compared some of our CBP general screening methods with the GUARDS method, and we began preparations to perform the GUARDS method verification. This is the overall process that we followed to verify the GUARDS method. Just a note, I'm just one of the chemists among several LSS personnel that were involved with this method verification process at CBP, and I'm here to share our experiences with you. So CBP decided to perform the GUARDS method verification after attending DEA's presentation. At that point, DEA supplied us with instructions, tips, method parameters, templates, and materials to perform the verification. DEA's complete package simplified the process for us. There was no need for us to reinvent the wheel and or duplicate efforts that had already been done. We started by configuring an instrument to run the GUARDS method, and we reviewed the acceptance criteria. Then we ran the standard mixtures over the course of 6 weeks, analyzed the data, plugged the results into templates, and evaluated our results against the established acceptance criteria. Finally, we wrote up the verification package and submitted it for review and approval. We are currently in the process of having other LSS labs perform the verification process with the goal of disseminating the GUARDS method to all of our labs. For our verification, we use an Agilent 7890 GC and 5977 MSD with a hydroinert source. However, other models and instruments from other manufacturers should be able to perform the GUARDS method verification. The GCMS we chose to perform our verification on was originally configured to use helium as a carrier gas, and it had been running helium for about 4 years. We converted the instrument over to hydrogen before we decided to perform this method verification. I'll briefly describe what we did during our conversion process. So we replaced our old gas lines with stainless steel, replaced our general GC consumables, including inlet parts and filters. We did replace our original extraction source with a hydroinert source, and we connected the instrument to our hydrogen generator. Since most of the parts in the flow path were new, there wasn't much buildup for the hydrogen to push out or cling from the internal parts. The baseline was initially higher and a little bit dirty, but after letting hydrogen run through the instrument for a couple of days, it was looking pretty much back to normal. So by the time we decided to perform the GUARDS method verification, all that was left for us to do was install the DB35 column and program the new method parameters, which are shown here. DEA's instructions also included steps to optimize our Agilent S-Tune for hydrogen. You can see the importance of this in the peak profiles I have here. The profile on top was the result of running an S-Tune with the default values, where the maximum repeller voltage was set to 20 volts. You can see that the peaks are jagged and split, especially the 502 ion, which is the ridermost peak shown in green. The profile on the bottom was produced after following DEA's instructions to increase the maximum repeller voltage from 20 volts to 30 volts using the Tune Wizard. You can see that the peak shapes improved, and as mentioned in previous presentations, this change had other benefits. The acceptance criteria for this method was provided to us by DEA. It was in their validation package, so this step was already completed for us. To recap, the acceptance criteria consists of selectivity or specificity, repeatability, and reproducibility. For selectivity, we look for single peaks with non-splitting apexes, minimal fronting and tailing, minimum retention times of 1.09 minutes, minimal signal-to-noise ratios of 3, and that all compounds could be identified by mass spectral comparison to a library entry or a reference standard spectrum. For repeatability, we compared the retention time of the first injection to the retention times of each replicate injection and looked for absolute differences to be less than 0.05 minutes. We also compared the relative retention time of the first injection to relative retention times of each replicate injection and look for the percent differences to be less than 1%. For reproducibility, we compared the retention time of the week 0 injections to the retention times of each subsequent week's injections and look for absolute differences to be less than 0.05 minutes. We also compared the relative retention time of the week 0 injections to the relative retention times of each subsequent week's injections and look for percent differences to be less than 1%. In summation, for each compound, we checked the quality of the chromatographic and mass spectral data, that all retention times were within 0.05 minutes of the first injection, and that all relative retention times were within 1% of the first injection. So, DEA provided us with 3 standard solution mixtures and solvent blanks for the method verification. Accompanying these materials were documentation about how they were prepared, which include manufacturer names, lot numbers, and weights and volumes used. Once we received the solutions, we dispersed them into individual GC vials to be run over the course of 6 weeks. DEA prepared each of these solution mixtures. Many of the concentrations are approximately 1 milligram per milliliter, except for the fentanyl low-level marker in the ethyl acetate mixture, which was approximately 0.05 mg per mil. And the exact concentrations for each compound were detailed in the accompanying documentation. The ethyl acetate mixture contains a variety of compounds that encompass a majority of the runtime, so there's early, mid, and late eluting compounds. The isomer 1 mixture contains diastereoisomers or diastereomers of amphetamine and methamphetamine, which are derivatized with MTPA chloride. The isomer 2 mixture contains the ortho, meto, and para positional isomers of chlorofentanyl and fluorofentanyl. Both the ethyl acetate and isomer 2 mixtures contain tetracosane as an internal standard. So this was our process for injecting the 3 standard mixtures and blanks over the course of 6 weeks. We decided to complete the longest sequence of the verification first. So we made 30 replicate injections of the ethyl acetate mixture, followed by 30 injections of the isomer 1 mixture, and finished with 30 injections of the isomer 2 mixture. To ensure that the contents of a single GC vial didn't evaporate after being repeatedly punctured, we dispersed each standard mixture into 2 GC vials, and we injected them each 15 times. In hindsight, it doesn't look like that was required, but it seemed like a simple step to take to safeguard against emptying a vial mid-run and having to rerun them. Also, between every standard mixture that was injected, we injected a solvent blank. In total, this was about 185 injections. So we programmed the sequence into the GCMS and let it run. After that, we injected each mixture once per week for 6 weeks. So each of these mixtures were also separated by blank injections, and that was only about 7 injections per week. Since these sequences were very short, they could be completed within a normal workday. So after the sequence finished, we replaced the caps on the GC vials and then stored them in our freezer. The next few slides will contain examples of our resulting data. As you'll see, some of the peakless areas of the chromatograms were cut out. That's just so that we could make relevant portions of the chromatograms easier to see than the ones shown here. For all of our data, we used the mass spectral interpretation software that came with our instruments to integrate, identify, and visually inspect each peak. We recorded the relevant information in spreadsheets that were provided to us by DEA. A portion of the spreadsheet is shown here on the left. After inputting the retention times and signal-to-noise ratios of the compounds into the respective cells, the template performs some calculations and output a pass-fail indicator in an adjacent cell. That cell's not shown here, but every criteria passed. The results shown here represent our ethyl acetate data and include some of the specific information that were used to evaluate the selectivity criteria, which again passed. The vertical blue bars on the chromatogram indicate where a section was removed. These sections didn't contain any peaks, and removing them just allowed us to enlarge the relevant portions for better visibility. So we found that each peak eluted with clear, non-splitting apexes and had minimal fronting and tailing. DMSO was the earliest eluder in the ethyl acetate mixture at around 1.3 minutes. That satisfied the minimum criteria of being after 1.09 minutes. The signal-to-noise ratios all exceeded 3 to 1, even the low-level fentanyl marker, which was at around 34. And every compound could be identified by mass spectral comparison to a library entry or reference standard spectrum. So in our experience in identifying the peaks, it was that each compound was identified by comparison to a library entry produced by the mass spectral interpretation software. We didn't have to comb through any hard copy or PDF mass spectra for manual comparison and identification. So these results are representative of the two isomer mixtures and include some of the specific information that were used to evaluate the selectivity criteria. The derivatized diastereomers of amphetamine and methamphetamine are shown on the left, and the positional isomers of chlorophenol and fluorofentanyl are shown on the right. Like the compounds in the ethyl acetate mixture, each compound in the isomer mixtures also passed the selectivity criteria concerning peak shape, elution times, signal-to-noise ratios, and mass spectral comparisons. This slide is a good visualization of how we saw the GUARDS method perform when analyzing very similar compounds. Looking at the chromatogram on the left, the two leftmost peaks prior to 7 minutes are L-amphetamine and D-amphetamine. The two peaks on the right after 7 minutes are L-methamphetamine and D-methamphetamine. Then the chromatogram on the right, the three peaks on the left between 10 and 11 minutes are meta, para, and orthofluorofentanyl. And then the three peaks around 12 minutes are meta, ortho, and para chlorophentanil. In a later slide, I'll show a case study that shows the difference between running a mixture on the GUARDS method and what was produced by running in the same mixture on one of our CBP general screening methods. Our experiences running the isomer mixtures and evaluating the selectivity criteria were good overall. The most time-consuming part for us was probably analyzing the data. Even that wasn't bad since the GCMS software automates a lot of that process. So after we completed the injections for selectivity, we began working on repeatability. This data is from the 30 replicate injections of DMSO in the ethyl acetate mixture. A representative chromatogram of the DMSO is shown here. We used the first injection as a baseline for comparison to each replicate injection. In all cases, the absolute difference in retention times ranged between 0 minutes and 0.01, which met the established acceptance criteria of being less than 0.05 minutes. Then we compared the relative retention time of the first injection to each subsequent injection. In all cases, the percent differences range from 0% to 0.8%, which met the established acceptance criteria of being less than 1%. Our experiences for performing the repeatability portion of the verification were similar to our experiences from selectivity. We just had to plug our resulting retention times into the spreadsheet supplied by DEA. We let the spreadsheet calculate the differences, and it output pass-fail indicators for each injection. The pass-fail indicator, it's not shown on this slide, but each result, pass or fail, appears next to the evaluated value. After running the repeatability portion of the verification, we started on reproducibility. This data shows the weekly injections of the isomer 2 mixture, specifically results from the chlorophenol peaks, whose representative chromatogram is shown. The elution order for the chlorinated isomers is meta, followed by ortho, then para. Injections made during the first week were designated as week 0 and were used as a baseline for comparison to subsequent weeks' injections. The absolute differences in retention times between the first and each subsequent injection range between 0.005 minutes and 0.01 minutes, which met the established criteria of being less than 0.05 minutes. The percent differences of relative retention times between the first and each subsequent injection range from 0.02% to 0.1%, which met the established acceptance criteria of being less than 1%. Our experience with running the reproducibility portion of the verification was not significantly different than either of the other portions of the verification. Again, we plugged our retention times into the spreadsheet, let the spreadsheet do some calculations, and then received outputs of pass-fail. So as we were writing up our verification package for submission and approval, we encountered a sample in routine analysis. We thought the mixture contained within the sample would be a good way to highlight the capabilities of the GUARDS method, so we created the case study presented here. The sample material in this case study contained a mixture of ADB Anaka and ADB Butanaka. The structural differences between the two compounds can be seen here. The structure of ADB Anaka is on the top chromatogram. ADB Butanaka is on the bottom chromatogram. You'll notice on the right side of each molecule, the ADB Butanaka has a butyl group, where ADB Anaka does not. So we completed our normal process of identifying the compounds within the sample and reported the results. Then we made a solution by combining the reference materials of both compounds. For comparison purposes, this solution was run on our current general screening method and on the GUARDS method. Some of the key differences between the two methods are listed on the slide, but it includes the type of carrier gas used. The CBP method used helium. GUARDS uses hydrogen. The CBP method uses an HP5 column, where GUARDS uses a DB35. GUARDS has 6 temperature ramps, ending at 340 Celsius. It incorporates a flow ramp. CBP method has 1 temperature ramp, ending at 300 Celsius, and no flow ramps. The final run times are also different. CBP runs for about 22 minutes, and the GUARDS method is 15.2 minutes. So to compare the results, the top chromatogram is from the CBP general screening method. At first glance, there appears to be one peak, but if you zoom in on the peak, which is shown within the ellipse, you can see that the apex of the peak is split, and that the ions that comprise the total ion chromatogram form 2 distinct peaks. The bottom chromatogram was produced by running the same mixture using the GUARDS method, where it's much easier to see that there are 2 compounds present because both peaks are completely separated. So in this case study, the GUARDS method allowed for easier identification of both compounds than our current general screening method, and would have been a pretty decent time saver. In summary, this is the timeline of our milestones achieved during the GUARDS method verification. CBP attended a brown bag colloquium hosted by DEA in April of 2024. At the time, CBP and DEA were collaborating on a separate effort, which led to CBP's involvement. Over the next month, CBP received the method parameters from DEA, along with instructions for performing the verification. CBP procured the instrument column specified in the method, coordinated transfers of the sample solutions from DEA, and configured and optimized our GCMS. The following 6 weeks were spent running the 3 solutions on our GCMS to assess selectivity, repeatability, and reproducibility. We spent approximately 2 to 3 months analyzing and compiling data, writing reports for the verification package. A portion of that time was due to balancing our regular duties with the verification efforts. We provided our verification results to DEA Special Testing and Research Lab, and we submitted the verification package, which is being routed through our approval processes. Our experience with adopting and implementing the GUARDS method at CBP LSS have been positive. We're not done disseminating GUARDS to all our labs yet, but it's planned. Overall, the package provided to us by DEA, which included instructions, method parameters, templates, tips, materials, and documentation, simplified the process for us greatly. We ran the mixtures over the course of 6 weeks, which didn't require a lot of dedicated time. Typically, one chemist would take the solutions out of the freezer, load them into the auto sampler tray, and start the sequence. After the sequence finished, someone would put new caps on the GC vials and place them back into the freezer. We analyzed all our data using the same software that we use for routine casework, so there was no need to learn another software. We visually checked the quality of the chromatograms and verified the mass spectral data. We input our results into the spreadsheets that DEA provided. The spreadsheets did some calculations and output pass-fail indicators for every value being evaluated. During the verification process, we did not experience any values that resulted in failed criteria. The entire process was very smooth. As I mentioned before, the verification package is currently being routed through CBP's approval process. So these are some of the next steps for the GUARDS method at CBP. Our New York laboratory plans to begin their own method verification in January of 2025. New York Lab's verification efforts will include adoption of the GUARDS method on 6 field lab GCMS units and 2 forward operating laboratory GCMS units. Once adoption has been successfully demonstrated in New York, the method will begin to be disseminated to CBP's remaining field laboratories and forward operating laboratories. Thank you for attending this presentation. If you have any questions, feel free to use the email address listed here. It's lab-interdict@cbp.dhs.gov. We would like to thank the DEA Special Testing and Research Laboratory for providing us with everything we needed to perform the GUARDS method verification, including their expertise. You provided just about everything we needed, except for an instrument to perform the verification on. I'd also like to thank all the CBP analysts and advisors that helped with the method verification, especially Gracia. Thank you all.
Thank you, Andrew, for such an informative presentation. Thank you all for this morning's presentations. Please feel free to reach out to us with any additional questions. Our next presentation is going to be from Kirk Lockett, GCMS analysis of street drugs utilizing hydrogen carrier gas in combination with a hydroinert electron ionization source. Kirk, take it away.
All right. Thank you very much. Okay, well, let's get started. I know a lot of times, people wonder, well, what's the big issue with hydrogen? And, a lot of people know that, we've used hydrogen as a carrier gas for decades. And for standard GC detectors, it's, usually not a problem. There's a lot of things you can adjust for. But when you use it for mass spec, there's a lot of things that you have to consider. Obviously, the first one is that hydrogen is very reactive. And because of that, it reacts with everything that it comes in contact with. And that's everything from the carrier lines that are coming from your source of gas, through your regulator, your EPC modules, your inlet, your column, all the way into your source. And so everything that it comes in contact with, it has a tendency to react and or basically what we call clean everything. It changes the surface of everything. And you don't have to have a hydroinert source to run hydrogen. I do want to make sure that everybody understands that. However, some of the problems I'm getting ready to mention are minimized and mitigated to a degree when using a hydroinert source. So you could use a stainless steel source, you could use an inert extractor source, or just an inert source to use hydrogen as a carrier for GCMS. However, the hydroinert, which is hopefully what I'm going to show you, does help, like I said, to mitigate some of these issues. In going into hydrogen, you want to use, normally what we found is a 9mm extractor or draw out, depending upon the flavor of mass spec source that you're using, to get the best results to minimize reactions that can occur in the source. Again, the other thing you have to remember is that hydrogen can react with every solvent, every analyte, every matrix, and so you do need to validate your method. And again, this is not anything that's new. This, is something that's been out there for a while, but a lot of people aren't aware of some of the issues that occur when you use hydrogen as opposed to helium. It can affect your chromatography. Also, with hydrogen, you may need to change your column configuration. In other words, go to a more narrow column for to have head pressure in your inlet. Hydrogen has a tendency to be a little bit less responsive as far as on your analytes go when it comes to ionizing. And again, there is always the possibility of having reactions and things that can go on throughout your entire system, things in your inlet, your liner, your column, all those types of things. And again, in my opinion, the best thing to do is if you don't have to go to hydrogen, don't. I mean, that's basically the way the system, I think, is set up. Helium, I know, has gotten very expensive, and I know there have been issues with availability. I think a lot of those have started to change, and it can be very cyclical as far as what's available and when. So, it is something that you have to consider. Again, my standpoint is that if you don't have to change to hydrogen, don't, because one of the big things that can be affected is spectral fidelity, which is going to affect your quality library match. And so if you are going to do this, just know that you're going to need to take time to validate your method. And again, one of the things that the hydroinert source does is help minimize some of that spectral infidelity that you get with the library matching. So the hydroinert source was introduced by Agilent about 2 years ago. I think it was at ASMS. And I had not used the source before then, and so I thought this might be something interesting to do with the forensics realm, which that's what my background is. And so some of the things I wanted to look at in comparing an inert source to a hydroinert source is the tuning. Obviously, if you can't tune the instrument, it's not going to run very well. So looking at the tuning, looking at reactivity with specific functional groups on a lot of the different drugs that are out there, does the source change in reactivity or its inertness over time? Is the spectral fidelity actually improved? Is it the same? Does it get worse depending upon the compounds and their overall analyte response? So these are some of the main focal points that I looked at. Again, another one is whether you're running in split or splitless mode, what type of solvents that you're going to use. Does a halogenated solvent affect the system or affect the source and its inertness? And a big one, too, is are you going to have to spend more time doing maintenance? And so, again, these are kind of the main focal points that I looked in determining what to look for, the certain parameters in the hydroinert source. And then I had certain analytical criteria that I wanted to do, again, knowing somewhat in the forensics realm. I don't consider myself a forensic expert by any means. It's been way too long. But I do know some of the concerns that they have and some of the things and parameters that they would like to operate in. And so I wanted to make sure that the method I use, I would be able to see buprenorphine, phenoxyacetylfentanyl, which is a late eluter, and again, a lot of those steroids like sildenafil and stuff that want to come out late. I also wanted to be able to separate amphetamine and phentermine and meth. Again, look at that splitless inlet, and I used an inerted inlet for this study, for this app note. I wanted to compare spectra under helium to hydrogen. And I used a helium method that I had developed previously for other applications and translated that helium method into a hydrogen method. I did use retention time locking. I used PCP as my locking compound. And as we go down the list, you can see I tried to tune it at A-tune, E-tune, S-tune at different temperatures. I try to tune once a week to, again, try to mimic what I think a lot of our customers do. And I had actual forensic samples, which was nice, so I'm not just running standards. I had about almost 40 methanol dilutions and about 80 acid-base DCM extracts that I was using. Did a ton of injections, over 2,500 injections with the samples and the cases and the standards that I had. And then analytically, as far as doing data analysis, I used unknowns analysis, part of Mass Hunter, and used deconvolution as the software. Also used NIST 20 and at the time SWIG-drug 3.8. So that's kind of the criteria that I used. Won't spend a whole lot of time on this slide. There is a PDF of the presentation if you would like that. That can be provided. But this is my helium method that I based the hydrogen method off of. It was a 14-minute run, and I did my hydrogen method and translated it into a 10-minute run. A little bit less than 10 and a half minutes. And one of the things to point out as well is that I used a single tapered bottom fritted liner and injected anywhere between a half to a microliter, and was normally running about a 20-to-1 split on my samples. So that first point of the tuning and how stable tunes were, this project went from July to March, from 22 to 23, and this slide really is just showing you the stability. If you look at some of the numbers as far as the EM, the repeller, the extractor lens, overall number of peaks and abundances, isotopic ratios, things look pretty similar from July to March using A-tune. And did the same thing with the E-tune, again, looking very stable, very reproducible as far as that goes. S-tune, hydrogen has a little bit harder time with S-tune. You've got to do some adjustments as far as with your multiplier voltage or your extractor lens. I just used straight S-tune. I did not make any adjustments whatsoever. That way, keep everything above board as far as just using the S-tune macro, and allowed it to tune. And it did pass, but it does have sometimes issues with the 502 abundance and that isotopic ratio. So one of the things that I mentioned in the very beginning of this was the reactivity of hydrogen, and this is one of the things that can occur with a non-hydroinert source. The top tick of the nitrobenzene on an inert extractor source, or it could also be a stainless steel source, you get reactivity on the surface with hydrogen. And what you're having is a hydrogenation reaction where that NO2 group is being kicked out and replaced with the NH2, with the hydrogen kicking out those oxygens. And so what that ends up doing is changing your spectra and getting poor library match scores. With the hydroinert source, you can see that your chromatography looks better, and you're not getting that reaction that's occurring with the aniline, with going into aniline with the nitrobenzene. And also note, these are both using 9mm extractor lenses. So one of the first things I wanted to do, I used nitrobenzene as an injection and a reactivity check about every 50 injections. But I also wanted to see what some of my nitro groups on some of the drugs. And so one of the first things I pulled and ran was clonazepam. And the top spectra is under helium. The bottom is under hydrogen. This is a library match score. And if I would have had a hydrogenation reaction occurring, I would have gotten 7-aminoclonazepam, which I did not see anywhere in the tick. So a good check for that. And so I went to next was the old standby, cocaine, and got a head-to-tail comparison of it, and again a library match score, pretty much apples to apples as far as library match score between running under helium and running under hydrogen with the hydroinert source. Methacrylfentanyl, again, pretty much with the head-to-tail comparison of the spectra. Again, the helium on top and the hydrogen on the bottom, good equal library match scores on that. I also, previous life, used to do a lot of explosives and chemical weapons, and so I pulled in some of my peroxides and looking on the inert source using eTune, library match score of TATP of 84, and then with the hydroinert source, library match score of 95. So that really did help to not only give me good spectral fidelity, but also you can notice up in the left-hand corners, I've got more analyte response as well, because remember, that's one of those issues that can occur with hydrogen on a non-hydroinert source. Also, again, went to the 4-nitrotoluene, which a lot of times is a byproduct and intermediate of some of the explosives. Again, a better library match score than just on the inert extractor source under hydrogen. And again, one of the other points that I wanted to do was determine over time, is this going to lose its reactivity as far as nitrobenzene being one of those known compounds that does react on the source if it's not hydroinerted. Is that going to happen over the process of, say, a sequence or running hundreds or even over 1,000 samples? And so what I did was run nitrobenzene, as I mentioned earlier, about every 50 injections, and found that after running almost 1,500 injections, I really had a very good library match score for my nitrobenzene. And actually, even when my nitrobenzene, as you'll see in one of the later slides, I start to lose it chromatographically, it's just a real ugly peak. I still had a very good spectral quality, so very low abundance, and this was an indicator that my system was getting dirty and I was needing to do maintenance, but I still had a very good quality match score on the nitrobenzene. So pulled some of the samples and just kind of randomly pulled out different drugs that I found in different cases. And in this instance, I used 11 different compounds. On the left side is a helium carrier with an inert extractor source and hydrogen carrier on the right with the hydroinert source. And what I did was the colors on the right, which are under hydrogen with the hydroinert, the green are responses that were actually higher than what they were under helium. The orange compounds were roughly the same, not a huge difference. And the yellow is where I actually had a little bit less response and again, this is from actual casework. So concentrations really kind of unknown, but this is also under Atune with an EM gain of 1 and using the Agile 2 integrator for integration of those area counts. So again, a pretty good comparison, quite a bit of increases in response and sensitivity, but the next thing was looking at its spectral integrity and spectral fidelity. And so I have, again, another mix of different compounds from various cases and under different tunes because I wanted to see if the tuning of the instrument affected the overall spectral fidelity of the compounds. And so in running Atune under helium and under, not under helium, but under hydrogen, under NIST 20, Atune, eTune, and S-Tune. And then on the right, we've got the SWIG drug 3.8. That's what was currently out at the time. And looking at those comparisons. And the one thing that stands out is under the S-tune, because of the algorithm of S-tune, and it has a very tight window of what masses it sets and abundances for 69, 219, and 502. It had a tendency to not detect some of these compounds when S-tune was run. However, it was never in an instance where a sample would have been called negative, because these were compounds that were in the baseline. A-tune and E-tune picked them up in the baseline. S-tune had some problems. And again, you can adjust S-tune, but I did not. I wanted to keep everything just straight with the algorithm. So again, something to be aware of. I wanted to look and see how things were stable over time as far as their spectral quality and their fidelity. And so I had a heroin standard that was about 10 nanograms on column, just as a comparison of a head to tail, and looking at a forward and reverse match of 923 and 926 on the reverse match. And then after running about 1,500 samples, this is actually a screenshot of my Excel spreadsheet, and again another head to tail with a sample that had heroin in it, and again a good quality match of 919 and 925 reverse. So good stability over at least, like I said, the 1,300, 1,500 injections. One of the things that I had heard other customers that had been using hydrogen in the past said that they had seen some issues when it came to whether you're running in split or splitless mode. And so hearing that, I wanted to investigate that, so that was one of my focal points. And so again, like I said, I ran most things at a 20-to-1 split, and so this is on the slide you're seeing right now is codeine on the left and morphine on the right under under helium, and in split mode. And we have a little bit of an opiate analog coming out with codeine at a 20-to-1 split. This was about a mg per mil. I wanted it concentrated on purpose to get as much as I could in that inlet, even with that 20-to-1 split. And because I know a lot of times our customers don't know how much they're injecting, because they're not exactly sure, what all is in it, what it's been diluted with, how concentrated it is. So that was kind of on purpose. And then when I did a splitless injection, there was a little bit of hydrocodone, and you may be able to see it in the very bottom between 9.6 and 9.8 minutes. There's a little red line there, but not really very much. The other peaks that are there are either just garbage peaks from just zooming into the baseline, or they're the opiate analog, like I said, that's at 9.7. But again, everything else not really present. Same thing with the morphine, nice clean peak, 20-to-1 injection. Had a little bit of codeine come out with the morphine, and again, some of the background, the peaks and stuff that you see there are really just contaminants in the system, not in reactions that are occurring because of the opiates that are in the inlet with helium. Now with hydrogen, I'll get it right this time. With hydrogen, did a split injection with codeine, and you can see a splitless injection produced hydrocodone, a huge increase in some of the opiate analogs, and definitely reactions going on in that splitless injection. Same thing with the morphine under hydrogen, a split injection, nice clean baseline, but you do a splitless injection and you have hydromorphone that's forming there. So again, something to be aware of. I did not run a full research project on this. I just wanted to see, what was happening in the inlet. So just something to be aware of, that if you're running under hydrogen and you're doing split or splitless injection, something to investigate when you're validating your method. And then lastly, one of the things that I looked into was just overall maintenance. And one of the things that I definitely want to stress in this point is that I think hydrogen, especially with chlorinated compounds is a little bit harder on the system. I think there is going to be more maintenance. One of the things that I found was that the liner had to be replaced after about 600 to 700 injections. You can see the liner that I used on the slide and that dark material on top of the frit that it was catching from getting it onto the column. You can see the nitrobenzene that's in the bottom right tick that I still had a very good quality match there, but my chromatography and my response dropped more than an order of magnitude. And the same thing with the test mix that I have on the left side of the screen. Again, a lot of this is not extremely obvious unless you're really looking at it, but it's very important that you run a test mix or a probe mix to be able to exercise your system and know how it's running while you're running your sequence, so that you can minimize the amount of maintenance that you have to do. You can see on the 1,6-hexadiol that I lost response, lost some chromatography there. And so I would definitely recommend making sure that you have a good mix, that you can check your chromatography. If you have a critical pair, checking your resolution and responses during your analysis time. So I found that after about 600 to 700 injections, the liner needed to be changed. And then after about 1,300 injections on this study, I had to cut about 4 to 10 centimeters off the head of my column, which I thought was rather unusual. One, I don't remember doing that when I was doing drug chemistry, and I talked to a lot of my customers at conferences and asked them how frequently they do that, and a lot of them using helium as their carrier say they may do it once or twice a year. I had some customers, depending on how many samples they're running it, were doing it once a month or once every other month. And I had some customers that weren't doing it at all. But again, it seemed like for only 1,300 to 1,500 injections, having to cut the column seemed a little excessive to me and unusual. So again, want to point that out. There is an app note out there that myself and Alexis wrote it. The link is active. If you don't have the link, you can put in the 5994 number at our website, and that will pull up the application note. It goes through all the details of evaluating the hydroinert source for seized drug analysis. We do have other resources on the website, and one of the things that we're finding, because again, this has been out for about 2 years, is after so many thousands, anywhere from 6 to 8 or more thousands, and again, depends on the samples, depends on your solvent, there is going to have to be maintenance done on your source because you can't clean it. It is something that if you abrasively cleaned it, you're going to affect the reactivity of the source. And so just know that you are going to have to replace some parts and pieces as you use the source, depending upon, again, your solvents, your matrix, how much you're injecting, how many samples, and we have a very good manual on cleaning the source, but non-abrasively with solvents, and what you can do to determine and minimize and extend the life of your hydroinert source. One of the big things is what gas you choose, whether you use UHP hydrogen from a tank and or whether you use UHP hydrogen that's being generated from a generator. The big key is that you have your gas, no matter what your source is, dry, as minimum amount of water as possible, and clean. So if that means doing additional filters, keeping up with the maintenance if you're using a generator, these are all things that are just very important when it comes to keeping your system clean and having a good longevity with your hydroinert source. So just to kind of summarize everything, part of what some of my focal points, just kind of going back over those. All the tune algorithms tuned under hydrogen carrier. Like I said, S-tune lost some sensitivity, but you can increase that by playing with your gain, some of the voltages in the source. There's a lot of different ways, but again, I just ran the tune as it runs normally with the algorithm, not changing anything. I had good spectral fidelity under hydrogen with the hydroinert source using NIS-20 and the Swig drug 3.8. Had good response as far as analyte response, and then as you saw, there are even some analytes that actually increased in response as opposed to helium as the carrier gas. It didn't seem that using DCM has a huge effect, although I think that may have been why my liner was getting dirty a little bit faster and possibly cutting the head of my column. But again, overall, it really didn't affect the quality of the data. It just more affected the maintenance of the system itself, which, again, the liner after about 600 to 700 injections and then cutting that column. Lastly, like I said, depending upon the time, the number of samples that you're running on your source, you may have to replace some of the source parts or pieces, usually the ion body or the repeller or the extractor lens. Again, as I said in the beginning, if you don't have to go to hydrogen, my recommendation as a scientist is not, especially if you have unknowns, because you just never know if someone's going to create something or synthesize something that may, during the validation process, was fine, but that wasn't around during the validation. So again, my big thing is to make sure you have a second orthogonal technique if you're going to use hydrogen for GC mass spec data, and that's everything from another system with helium, NMR, FTIR, all the number of different analytical techniques that are out there. You just don't want to go and do a sole hydrogen, in my opinion, system and use that for all of your data. So with that, there are some resources out on the website. Again, these links are active. I checked them. Sometimes we have a tendency to move our stuff around, and these links are good. And again, how to set up for hydrogen, how to convert from helium to hydrogen, with a lot of good tips and tricks to help the process go a little faster. And I know we're going to have Q&A at the end, but that's it. Thank you for your time. I appreciate it. Hope it was informative to everybody.
Yes, thank you, Kirk. It was a very informative presentation. Our next presentation will be Hydrogen, Carrying the Future of GCMS by Courtney Mayhew. Courtney, take it away.
Hello, thank you. The title of my presentation is Hydrogen, Carrying the Future of GCMS. So this presentation will discuss the tools, resources, and requirements when considering converting from helium to hydrogen on Shimadzu GCMS systems. I'll go over the basics on how to convert from helium to hydrogen, as well as what other things you may need to consider during this process. So in recent years, helium shortages and increased price of helium have initiated the efforts for us to find an alternative carrier gas. Do you think that hydrogen is the carrier gas of the future? Well, there's often some hesitation when it comes to thinking about switching to hydrogen as a carrier gas. And the hesitation is for good reason. There are safety concerns because hydrogen is highly explosive, and the detector sensitivity will be about 2 to 4 times lower for all manufacturers because of the reduced vacuum pumping capacity. Hydrogen has a lower diffusion coefficient than helium, and so higher pumping capacities are required. Hydrogen is a reactive gas, and some compounds may be affected by hydrogen. Chemical reactions may occur in the inlet, source, or column, and some of these chemical reactions may interfere with library searches. So here's an outline of today's talk. I'll cover the tools that can be used to convert from helium to hydrogen. I'll go over the instrument safety features that will ease your mind about converting from hydrogen and what we have to offer to help with method development. I'll talk about the cost and availability when choosing a tank versus generator. And because of the detector sensitivity being 2 to 4 times less with hydrogen, I'll go over a direct comparison of helium versus hydrogen. And then I'll wrap up with a few Shimadzu application notes using hydrogen as a carrier gas. So let's highlight some of the different features available from Shimadzu GCMS instruments that will assist your transition to hydrogen. We'll cover these features in detail during the presentation. First is the hydrogen sensor. The hydrogen sensor is a safety feature that's added to the hardware. Our dual-stage pump provides efficient vacuum even with hydrogen. Next is our constant linear velocity as a carrier gas control mode, and we can see how this is a useful tool for hydrogen method development. We offer a gas selector that will allow you to switch back and forth between carrier gases if needed. And if the plan is to completely forget about helium, our collision gas does not require helium. So at the end of the transition, our instruments are helium-free. Finally, we offer smart databases, which are tools for method development. Smart databases are based on retention indices, which means it doesn't matter what carrier gas we have, creating a method for many compounds is simplified and time-saving. We are constantly working on ways to improve and innovate and create new applications using hydrogen as a carrier gas so we can offer a complete solution. So let's go over the hydrogen sensor. Safety first. As we mentioned, there are hesitations using hydrogen because it is a combustible gas above 4% volume in air. Typically, we are not concerned with hydrogen that enters the lab through a leak in the system. This is because the volume is exceedingly low in comparison to the high flow of the HVAC system. A high percentage of hydrogen will rarely ever be reached. Our main concern, however, is hydrogen that enters the oven through a break in the column. The oven is a small space and hydrogen can easily accumulate to 4% by volume in air. For this reason, Shimadzu offers a built-in hydrogen sensor that not only maintains a safe standby mode, but early detection of potential leaks. The hydrogen sensor also shuts off the main power to prevent accidents in the event of a hydrogen leak above 2%. The main unit also includes an automatic carrier gas leak check function, which is helpful when using hydrogen as a carrier gas. Commercially, there are 3 gas control modes: constant pressure, constant linear velocity, and constant flow. So why would we pick one control mode over another? The same chromatogram will be acquired for all 3 modes in isothermal analysis. However, this is not the case when data is acquired using a temperature program. And a temperature program is the most common way to perform GCMS analysis. If we look at the graph on the top right, we have the mean linear velocity versus column temperature. The constant pressure mode is shown in blue, which will decrease the mean linear velocity as the column temperature increases. While the constant flow mode is shown in green, this will increase the linear velocity as the column temperature increases. From this information, we can determine that in constant pressure or constant flow mode, the quality of the chromatography will vary along the chromatogram. It is important to review the Van Deemter plot when selecting the most appropriate carrier gas to have the best performance when working in specific ranges of linear velocity. To quickly review the graph on the bottom, the y-axis, we have the efficiency, or the height equivalent to a theoretical plate. On the x-axis, we have the linear velocity. The lower the efficiency, the better separation of the peaks. Nitrogen is shown in green, is only optimal at low linear velocities. But we see both helium and hydrogen have a broad range of linear velocity, where the height equivalent to a theoretical plate is at a minimum. So let's compare when using these 3 gases. Here is a comparison of separation of mixture under ideal conditions, except for the carrier gas type. First is nitrogen carrier, and then helium, and then hydrogen. The linear velocity is maintained at 35 centimeters per second, which would be near optimum value for helium, but well above for nitrogen and below for hydrogen. As we would expect, the resolution for helium is best. However, due to the low viscosity of hydrogen, the peaks elute slightly faster with helium. Faster linear velocity means faster analysis, and time means money. When using hydrogen as a carrier gas, the outlet pressure coming from the column tends to be a little higher than normal. So this adds the need for the pump to do a higher pump down, which can lead to a loss in sensitivity. The design of the turbopump of Shimadzu GCMS is a dual inlet turbomolecular pump, which maintains a dual zone vacuum, and as a result, maintains the performance at high pressure even when using hydrogen. The source and quads have their own differential stage of pumping, resulting in a better vacuum, which is more uniform throughout. As I mentioned earlier, when switching hydrogen carrier gas, there are no changes to the hardware configuration. Shimadzu GCMS comes hydrogen ready out of the box. With our stainless steel inert piping, nothing in the advanced flow controller is copper, and this means hydrogen. Since all the hardware is already installed, you can always switch back and forth to use any carrier gas options, and there are no additional gas requirements for the ion source, simplifying the gas input requirements. We understand the importance of having a helium-free system, and with the current cost and availability of helium, our GCMSs can accommodate. Our collision cell does not require the use of helium since argon or nitrogen can be used as a collision cell gas. In addition, our off-axis design reduces noise from non-targeted components, so we do not have to worry about any extra noise production. The chromatogram is a comparison of the noise production from a straight position design compared to our off-axis design displayed in pink. And we also understand that there are some applications that may not be suited to using hydrogen as a carrier gas. As an alternative, we offer the gas selector for customers who want to save on helium. The gas selector is a small hardware addition that offers the ability to easily switch between gases without the physical need of going and changing the tank connections. By having both a carrier gas and a substitute gas, the software can be set up to change the helium for either nitrogen or hydrogen when there is no analysis running. This is shown in the figure on the bottom left. The helium is used for batch analysis and then standby with nitrogen. Later, the software can have the instrument ready for the next analysis by changing it back to helium at least a half hour before, giving ample time for the instrument to stabilize. This is shown where helium is used for gas switching and then analysis, and then finally back to nitrogen during standby. This can result in a gas consumption savings up to 90% depending on the time that the instrument is performing analysis. In addition to those benefits, the gas selector can be useful for switching between analyses when working with methods that are suited to different carriers. It doesn't have to be just helium and hydrogen. It could also be nitrogen, as shown in this example. Method development is always the hardest part of implementing a new analysis in the laboratory. Because of this, we have smart databases to help ease the process. These smart databases are based on retention indices and pre-built methods that are included in the package. The databases are used regardless of what carrier gas we set up on the instrument, and it only takes a few steps to build optimal analysis method for targeted compounds. As I mentioned on the previous slide, the smart databases have retention indices for all registered compounds. Retention index is a measure of a compound's retention time normalized to the retention time of the adjacently eluting N alkane. A compound's retention index is based on thermodynamic principles and is correlated to its chemical structure, so this is unique to each compound for a given column phase. Shimadzu's automatic adjustment of retention times, or AART function, uses this relationship and provides a scale at which it adjusts the retention times. Using our mixture provides about 25 compounds for a multi-point correction covering a wide range of the chromatogram, and this is especially important with hydrogen. This is an example of how your retention times could shift moving from one method to another instrument or changing carrier gas. The chromatogram on the top is the originally registered method in the SMART database. The target compound is indicated by the star, and then the chromatogram on the bottom is when the method is used on the customer's instrument. The automatic adjustment of the retention time is indicated by the red arrow. Manually updating retention times and compounds can be tedious and could lead to incorrect peak identification, especially when you have many target analytes. The relationship is used in our SMART database to predict retention times. Running the alkane standard and applying it to the database, we can calculate the retention times of the target compounds, making method development quick and easy. This slide includes all of the available Shimadzu SMART databases to target different customer goals, including pesticide, environmental, forensic, metabolites, and aroma. Each of the databases includes a list of compounds and their retention indices, MRM and SEM ions, as well as recommended methods. Some of the SMART databases can only be used on triple quad, but some can also be used on single quad. If looking to use an alternative carrier gas with your instrument, consider the options with the following chart. The table lists each instrument and their corresponding hydrogen and nitrogen compatibility. We recommend hydrogen over nitrogen for most applications, as the linear velocity of hydrogen is more closely related to that of helium, making changes to the method easier to control. Care should be taken when switching to any alternative carrier gas to monitor for losses in sensitivity. Method conditions can be optimized to reduce the effects of switching over. Many of our samplers use flushing or pressurizing gas that isn't GC carrier. This table is useful when planning to use hydrogen as a carrier gas, but using a pressurization method, like with our HS20, where one can use nitrogen for pressure and purge. The table shows our most popular sampling equipment and the sampling and carrier gas compatibility with hydrogen and nitrogen. You can check out our Getting Started guide for more details on combining gases and optimal configuration. Now that you've made the decision to switch from helium to hydrogen, you'll have to decide between a tank or a hydrogen generator. After the initial cost of a hydrogen generator, the generator is a cheaper and safer option for hydrogen carrier. In addition, a hydrogen generator has a lower amount of hydrogen gas, making it safer to use than a hydrogen tank. The changes needed for the instrument are minimal when converting from helium to hydrogen. The system configuration for the injection port must be changed to indicate that hydrogen is being used. This will allow the GC to calculate the correct pressures for the GC. It is also recommended to perform inlet maintenance and possibly replace gas filters when changing to hydrogen to minimize downtime. If further improvement to the chromatography is required, a tapered liner should be considered. The density and viscosity of a gas will dictate how it moves through the column, so you will need to modify your method to accommodate for this. There are many tools that are available to help with converting method parameters from helium to hydrogen carrier gas. A useful and functional tool is called the EZGC Method Translator and is available for free on ResTech's website. You just have to create an account. It will determine new pressures and oven temperature parameters that are needed, as well as give options on whether you want a direct translation or a method that will give you the fastest and most efficient method. Please be aware that while the EZGC tool is very effective at giving a good translation for methods from helium to hydrogen, some further method optimization may be needed to improve chromatography, especially if there is significant coelution issues. So let's talk about some performance with hydrogen. So what compounds may not perform well with hydrogen? Compounds that will be reactive and compounds that can break down easily. Other things to keep in mind is that the spectral results should remain constant, but you should always confirm when using hydrogen. The performance will vary depending on the analyte of interest, but the signal to noise is often 2 to 4 times lower than with helium. Now let's compare the chromatography. Here is a side-by-side comparison of a chlorinated pesticide at 2 ppm. And on the bottom, you can see that the retention times are earlier with hydrogen. And you'll see the first peak is around 8.5 minutes. And then for hydrogen is about 11. And for about 11 for helium. And you can still see that we still have good resolution with hydrogen. And we'll take a look at an overlay comparison on the next slide. With an overlay comparison of the same fluorinated pesticide, we can look at sensitivity and how does the data compare between helium and hydrogen carrier. There's typically some loss in peak area, usually around 20 to 40% depending on the application. But the peaks are typically sharper and the baseline noise is lower, so the sensitivity loss is about 20% for a typical pesticide run. Keep in mind that the precise method development regarding the column flows and temperatures can improve this. Here we see a depiction of reduced retention times and comparable calibration curve linearity for some selected pesticides. The table shows the R-squared and retention times for helium and hydrogen. The retention times are decreased using hydrogen with similar resolution, and for the linearity is comparable to what can be achieved with helium. The runtime is decreased, increasing the sample throughput. So here's an example of an application note from Shimadzu using a hydrogen carrier gas. In this application, a simultaneous analysis of pesticides was used on single-quad GCMS with hydrogen carrier gas. Calibration curve was prepared of pesticides, was prepared at concentrations of 0.05 milligrams per liter to 0.5 milligrams per liter containing 59 pesticides. This method was created using the ResTech EasyGC method translator and also used the trace hydrogen generator as the source of hydrogen carrier gas. The column length was changed from 30 meters to 20 meters, and the analysis time went from 30 minutes with helium to 20 minutes with hydrogen. The repeatability results for 5 replicates at 0.01 milligrams are shown in Table 3, and favorable results were obtained for the percent RSD and R-squared values. Here's another application that uses hydrogen as a carrier gas for the analysis of phthalate using single-quad GCMS. For this application, they wanted to investigate any changes to the spectral pattern. 5 milligrams per liter was measured in scan mode, and there were no difference in the spectral pattern, which is shown on the slide. Since it has been reported that hydrogen carrier lowers the results of sensitivity, 0.05 milligram per liter was measured in SIM mode, and even at low concentrations, the signal to noise was 94. Calibration curve was generated using the concentration range, and this study demonstrated satisfactory sensitivity and quantitative performance. For the next application, VOCs were measured using our TD30R thermal absorption unit with single quad GCMS with hydrogen as a carrier gas. A mixed standard was prepared to create a calibration curve from 10 nanograms to 100 nanograms. The results were shown in the table and the calibration curve. Satisfactory results were obtained for linearity and repeatability, demonstrating it's possible to measure VOCs using this technique with hydrogen carrier gas. Our TD30 thermal absorption system supports hydrogen in addition to helium and nitrogen. Thank you.
Thank you, Courtney, for your informative presentation. And thank you to all the afternoon's presenters. We will now begin with the afternoon Q&A with the first question received from the audience. The question goes to Kirk. Kirk, can you use the hydro inert source with helium carry?
Technically, yes. I would not recommend it because, again, you can't clean the source abrasively. And so you can use it with helium carrier, but, I mean, why? I would not recommend doing that.
Okay. The next question, Courtney, I'll move to you. Is hydrogen sensor available to be added on a GCMS QP 2010, or is it only available on newer models like the 2030 or 2050?
Hi, no, that's only correct. It can only be added to the 2030 or the 2050.
Okay. All right, thank you. Kirk, why did you choose PCP as your retention time lock compound?
Actually, the main reason is that it comes out in about the middle of my run. And I have found over the years using retention time locking that finding a compound that comes out more in the middle of your run, my window as far as variation when I relock my system is a lot tighter. Technically, it doesn't really matter. You can have an early eluder or a late eluder, but I've just kind of found that if I do something in the middle of my run and I do the locking on it, that when I go back to relock it to do that one-time injection to bring everything back into the window, my window's a little tighter when I do that. So that's the main reason.
Okay. Kirk, in your study, did you find that there was an instrument detection limit for the hydroinert at installation?
For the hydroinert, I believe it's 50 femtograms on column for the IDL, for the instrument detection limit for a hydroinert system when it's installed.
Okay. Next question is for either one of you, either Courtney or Kirk. In your experience, how do pseudoephedrine and ephedrine perform under hydrogen? Do you see hydrogenation products?
Courtney, do you want to do that? Or I can either way.
Kirk, I think you might have more experience with that. If you want to take that one.
No problem. Sure. Actually, I myself have not run the ephedrine, pseudoephedrine, but I have talked to customers that have the hydroinert source and I have specifically asked them that, and they have said they have not seen any reactivity with those compounds as far as a hydrogenation reaction when it comes to ephedrine.
All right, thank you. Kirk, the person asking was told that the hydroinert source is considered a consumable and will need to be replaced since it cannot be cleaned. Is that true?
I wouldn't say the source itself is consumable. There are parts of the source. Again, the main parts being the ion body, the repeller, and the extractor lens. The source can be cleaned. It can't be abrasively cleaned. That's the key. You can solvent clean it and use cotton swab and clean the source surfaces of the various lenses as you do a regular source, whether it's stainless or inert. But you can't abrasively clean it. So you wouldn't be replacing the whole source. It's mainly one or two pieces of the source, one or two elements.
Can hydrogen carry be used on a stainless steel or a regular inert extractor source, or do you have to use the hydroinert?
I'm sorry, say that one more time.
Can you use hydrogen in stainless steel or regular inert extractor, or does it have to be the hydroinert?
Oh, no, most definitely. You can use stainless steel or inerted sources. Like I said, people have been using hydrogen on GC mass spec for decades. The key is that you have to deal with reactivity and all the things that Courtney and myself mentioned today of spectral fidelity and reduced responses and things like that. And the hydroinert source doesn't solve all of that, but it does help to mitigate it. It's not a silver bullet, but it helps to minimize a lot of the things you see with a stainless steel or an inert source.
Thank you. Courtney, do you recommend a hydrogen generator or a UHP tank of hydrogen?
I recommend a hydrogen generator just because it's safer, but if you're not going to be running it all the time, like us, it doesn't work out as well. But if you're going to be using it regularly and, making sure you get it taken care of the way it's supposed to be, it'll work well.
All right. Thank you. Kirk, do you have you ever used the 9mm extractor lens when using hydrogen carrier?
Yes, the 9mm is what's requested that you use when you start, and that's what the hydroinert has, is the 9mm extractor. We have a 6 and a 3. What I normally suggest is for customers is to start out with the 9, because the 9mm from a 6 obviously is a bigger hole, and so you do have a little bit less response. Usually about a half an order of magnitude of what I've seen for most drugs. And so that may not give you good abundance that you're used to seeing for, say, your QC mix. And so the next thing I would do is then go down to a 6 millimeter and see how that does. So there's flexibility there. We just recommend the 9 millimeter over starting with the 6 or even the 3 to see how it's going to work with your sample, your matrix, and your target analytes.
Kirk, you stated in your presentation that they may need to replace parts. How would a laboratory know which parts to replace? Is there a troubleshooting technique that you would recommend so they know which parts they would need to replace?
Well, what I normally do, and what I did in the study and in the app note, is again having a QC mix that you know what it looks like. You know what it looks like response-wise. You know what the chromatography should look like of the various compounds, and you're monitoring that because I try to keep everything simple and cheap. That's kind of my philosophy. It's something that I can fix and replace without digging into the instrument and get it back up and running, or is it something where I've got to vent and I've got to actually do something? So I would work through the process, first do the liner, the inlet, the column, and then with the source itself, I would normally what is going to come into most contact with things is the repeller and the extractor, and so normally I would replace the repeller and the extractor as a pair. And then if that doesn't bring the system back up, then the ion body.
All right, thank you. Courtney, can hydrogen be as a pressurization gas be used for headspace analysis?
So you can use the hydrogen as a carrier gas for headspace, but you need to use an inert gas for the vial pressure because it's very dangerous and it can cause an explosion.
And, Courtney, would hydrogen carrier gas affect the quality of library searches with the GCMS?
So our studies have shown that with the modern mass specs that there's no significant difference in the library searches that we've seen. You just should always double check and confirm.
Thank you. Kirk, you were explaining earlier about the different parts that you may have to replace in the hydroinert. On a hydroinert source, do you have any indication on how often certain parts will need to be replaced?
It's really hard to tell. It really depends upon number of injections, your matrix, levels of response. Like I said, it's been out for about 2 years now, and I've heard from customers anywhere from I want to say 6,000 to 8,000 injections or 8,000 samples. I'm sure there's others that have been higher, others that are using it and haven't had an issue. So there's a lot of parameters and factors involved. So, but it's well into the thousands.
Okay. This question is for both of you. We'll start with Kirk. Which solvents have you validated with hydrogen, and in your opinion, which is the best to use?
The only solvents I've used are ethyl acetate, methanol, and DCM. I haven't really done much with chloroform. I think the best that I have seen as far as just chromatography and response-wise for specific drugs is ethyl acetate, actually. I used to do toxicology, and that was actually a very, very good solvent, and it's a good GC solvent as far as that goes as well.
Okay. Courtney?
Yeah, we have some experience with hexane and toluene. Yeah, so that's kind of my experience with that.
All right, thank you. Courtney, why does hydrogen cause sensitivity loss in a QP 2010 SC system, but not as much in other systems?
Hi, yeah, so with the QP 2010s, they only have one turbomolecular pump, so it has to do with the pumping capacity, so it's not able to keep the sensitivity as it is on the dual turbomolecular pumps.
All right, thank you. Kirk, you stated abrasive cleaning. What is it that you consider as abrasive cleaning?
Oh, using aluminum oxide, using sandpaper. You can use, like I said, normally a cotton-tipped swab, but even then, you don't want to strong arm it. You just want to gently clean it with solvent.
All right, thank you. Are the parts that may need to be replaced on a source covered by a service contract, or is it responsibility of the consumer? This is for Kirk.
Well, it depends on the service contract. I'd say probably for most customers, not more than likely not covered. That's going to be a high-level service contract for your parts inside your source.
What are the signs that you would say are an indication that consumable parts of the source need to be replaced?
I'd say decreased response. When you're tuning the system, high mass, abundance, the isotopic ratios, like for between 502 and 503, their responses and their relative abundances go down. Trying to think, you could see some unusual fragmentation patterns as well. That ions and fragments that aren't normally in the spectra.
Thank you so much to both presenters. There are no more questions, so we're going to go ahead and wrap up today's workshops. Please, to the audience, feel free to contact any of the presenters. I do want to wrap up with saying that there are more and more studies that are being done with the use of hydrogen for cease drug analysis and all the different types of drugs. And more laboratories are switching to hydrogen. I do think that it would be up to the laboratory to do that type of research and see what is it that is the best fit for their operations and for the type of samples that they receive. However, if there's any questions in terms of the GARS method, please reach out to any of the DEA presenters. We're here to assist in explaining our validation and the process that we use and all the different substances that were analyzed and validated through our process. With that, I want to say thank you so much for attending this webinar, and to all of our presenters for being with us here today. Again, thank you for sharing your questions and your expertise with us.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.